Why does the night sky's darkness hide more than it reveals? What invisible force keeps stars in galaxies from flying away? Could most of the universe be made of something we cannot see? On a still, moonless night, you gaze upward and find yourself enveloped in darkness. The sky above is a vast black canvas, dotted with the soft glow of distant stars. The night air is cool and quiet. In that quiet darkness, the universe slowly reveals itself. With no city lights around, more and more stars emerge the longer you look, as if each minute of darkness draws out new secrets from the sky. The Milky Way arches overhead in a faint silvery band, a mist of countless stars too distant to distinguish. In the gentle dark, you can sense the enormity of space extending far beyond, an endless, calm expanse. In the daytime, the bright blue sky hides the cosmos. Only when night falls and the world grows dark do those faraway suns appear. Darkness, it turns out, allows us to see more stars, more of our universe. What at first seems like emptiness becomes, with patience, a gateway to countless lights. There is a peaceful paradox in the quiet night. The darker the sky, the more it reveals. It makes you wonder, in that darkness between the stars, what else might be there that our eyes cannot see? For thousands of years, people have looked up in wonder at this night sky. Ancient travelers navigated by the stars that shine like tiny beacons. Poets and dreamers found shapes in the starry patterns, imagined gods and animals traced out in constellations. Yet beyond the patterns of stars lies the dark backdrop of space itself, deep and enigmatic. Under that dome of darkness, generations have felt both curiosity and comfort, as if the night sky holds answers as well as questions. When you stare into the dark expanse, you might notice how serene it feels. The silence of space, the slow twinkling of starlight, it all encourages a kind of contemplation. In that contemplative mood, you might ask, what is hiding in the darkness? Is it truly empty between those stars, or is something unseen filling the void? For most of history, we assumed the dark was just an absence, a great emptiness separating the islands of light. But as our knowledge grew, we began to suspect that the darkness itself might be hiding more than anyone imagined. The quiet night sky, seemingly so still and empty, would soon become the key to one of the biggest mysteries in science. It starts subtly. Small discrepancies, faint hints that all is not as it appears. For a long time, they were easy to ignore. A star moving a little too fast here, a galaxy's rotation looking a bit odd there. Little puzzles lost in the vast night. But one by one, these puzzles collected, like pieces of an unseen picture. They whispered that the darkness wasn't empty at all. Something invisible yet powerful was out there in the dark, something holding and moving the stars in ways we couldn't see. This realization did not come all at once. It unfolded slowly, over decades of quiet observation and wonder. So lie back and picture the night sky again. Imagine the darkness between those stars is not just nothingness. Picture it as a gentle, unseen presence, cradling the starlight, guiding the dance of galaxies. The story of dark matter begins here, in the silent allure of the night. It's a story of how darkness revealed more than light, a story of hidden mass, cosmic mysteries, and the search to understand the unseen skeleton of the universe. Now let us drift deeper into that mystery. Decades before anyone suspected a cosmic mystery in the darkness, astronomers were already encountering odd little puzzles in the heavens. One of the earliest happened in our own solar system. In the 1840s, the planet Uranus wasn't moving exactly as expected. It wobbled slightly in its orbit, as if tugged by an unseen hand. A French mathematician, Urbain Le Verrier, and an English mathematician, John Couch-Adams, separately calculated that a hidden planet farther out could be pulling on Uranus. They pointed astronomers to the sky where this invisible influence seemed to come from. In 1846, a new planet was spotted near that very position, Neptune, gleaming faintly against the dark. It was a triumph of physics and intuition, a world discovered not by sight, but by its gravitational tug. The darkness had concealed a planet until careful observation revealed its presence. Emboldened by Neptune's discovery, Le Verrier turned his attention to another celestial oddity. Mercury, the tiny innermost planet, had a subtle quirk in its orbit. Its closest point to the Sun drifted faster than classical physics predicted. Le Verrier proposed that perhaps a small, unseen planet, which he named Vulcan, was orbiting even closer to the Sun and nudging Mercury's path. Astronomers eagerly searched near the blinding glare of the Sun for Vulcan's elusive presence. But no planet ever appeared. The mystery of Mercury's orbit lingered unsolved for decades, until a new idea, Einstein's general relativity, showed that space and time around the Sun were curved, accounting for Mercury's motion without any hidden planet at all. In this case, the solution to the puzzle was a revolution in physics rather than a new object. It was a humbling lesson. Not every irregularity meant something unseen was out there. Sometimes it meant our understanding needed to deepen. Even so, the notion that invisible things could be lurking in the dark gained a foothold. Astronomers began to realize that many stars might have unseen companions. The famous star Sirius, the brightest in our night sky, was observed to wobble slightly, as if influenced by a partner star too dim to see. Sure enough, in 1862, a faint white dwarf star, later called Sirius B, was finally spotted next to Sirius, confirming the prediction. All across the sky, more binary star systems were found, where one star was bright and the other dark, detectable only through its gravitational pull on its visible partner. The universe was revealing a pattern. Time and again, things we couldn't see directly were making their presence known by the subtle effects on things we could see. Astronomers grew more comfortable with the idea that space might be filled with hidden objects, dark moons, lost planets, burned-out stars, quietly influencing the visible world. By the early 20th century, scientists were taking inventory of the cosmos with this in mind. Some wondered if the Milky Way galaxy might hold vast numbers of dim stars or invisible matter. The eminent physicist Lord Kelvin, in the late 1800s, even calculated that the motions of stars suggested far more mass than the stars we could observe. He spoke of dark bodies filling space, perhaps outnumbering the bright stars. These ideas were largely speculative and didn't immediately reshape astronomy, but they planted seeds of curiosity. For the most part, the cosmos still seemed to behave as expected. The planets followed their predicted paths, save Mercury's slight deviation, and the stars' motions made sense once allowances were made for the occasional unseen companion. There was no urgent sense of crisis or mystery. Yet, quietly, the stage was being set. The methods and mindset to find the unseen were established. If a celestial object's motion was strange, astronomers knew to ask, "Is something hidden out there?" This question would prove vital when our gaze extended beyond the nearby stars and planets. As telescopes grew more powerful, we began to observe the motions of entire galaxies and the stars within them. And here, in the swirling forms of galaxies and clusters of galaxies, the old question of something hidden resurfaced on a far grander scale. The early hints were subtle and easily dismissed, but soon they would become impossible to ignore, ushering in a deepening mystery that went beyond any lone planet or star, a mystery that would force us to rethink the very makeup of the universe. By mid-century, our telescopes and instruments had grown powerful enough to study not just individual stars, but the grand spinning disks of entire galaxies. A spiral galaxy, like our neighbour Andromeda, or even our own Milky Way, rotates. Its billions of stars orbit around the galactic centre. Astronomers expected that, much like planets in the solar system, the outer stars in a galaxy would orbit more slowly than the ones near the centre. After all, most of a galaxy's visible mass, the stars, gas, and dust we can see, is concentrated toward the centre. Beyond a certain point, there seemed to be very little out there, so the pull of gravity should weaken and orbital speeds should drop off with distance. In the 1970s, astronomer Vera Rubin and her colleagues set out to measure how fast stars and gas move in the outer regions of spiral galaxies, using sensitive spectrographs to observe the Doppler shift of starlight. They mapped the rotation speeds at various distances from the galactic centre. What they found astonished them. One can imagine Vera Rubin, in the quiet of the observatory, examining her data late at night. As the measurements came in, she plotted the rotation curve of a spiral galaxy and saw the line flatten out instead of dropping. It was a subtle, almost eerie revelation. The outer stars were orbiting too quickly, as if held by the gravitational pull of something invisible. The universe, it seemed, was whispering a secret through those starlight measurements. Instead of slowing down far from the centre, the stars in the outer parts were moving just as fast, sometimes even faster, than those closer in. The rotation curve, a plot of orbital speed versus radius, was nearly flat. It was as if the galaxy had far more mass out in its outskirts than anyone had anticipated. Mass that wasn't visible in the form of stars or gas. This result was puzzling and a bit unsettling. If the only matter in the galaxy was the matter we could see, the glowing stars, the hot gas, the shining nebulae, then those outer stars should not have enough gravity to hold them in their orbits at such high speeds. By rights, they should be flung off into space by their own momentum. But they weren't. Something must have been providing the extra gravitational pull to keep them bound to the galaxy. Rubin and others proposed that each galaxy is surrounded by a vast halo of unseen matter, extending well beyond the visible stars. This invisible halo contains most of the galaxy's mass, explaining why the outer stars feel strong gravity and orbit swiftly without flying away. At first, such a notion, that a galaxy is mostly made of invisible stuff, sounded extraordinary. Scientists are naturally cautious about claiming the existence of something new and unseen. Rubin's findings, however, were consistent across many different galaxies she studied. One after another, spiral galaxies showed the same phenomenon. A flat rotation curve, a clear sign that a huge fraction of their mass is hidden in the dark. Over time, skepticism began to fade as more observations confirmed these results. By the late 1970s and early 1980s, the term missing mass or dark matter was increasingly used to describe this mystery ingredient. It's important to note that hints of this missing mass had surfaced even earlier. As far back as the 1930s, a few astronomers had noticed oddities in galaxy behavior. though their work was largely overlooked. An astronomer named Horace Babcock, for instance, in 1939, studied the Andromeda galaxy's rotation and suggested there might be undiscovered mass in its outer parts. His data, however, were not precise enough to be conclusive, and the idea quietly slipped into obscurity at the time. It would take improved technology and systematic surveys decades later to truly reveal the extent of the discrepancy. When the evidence finally became undeniable, it was as though a veil had been lifted from our understanding of galaxies. We realized that the graceful spiral you see shining in the darkness is only the tip of the cosmic iceberg. Encircling each luminous galaxy is a vast, dark halo of matter that does not emit or reflect light, yet its gravity governs the galaxy's fate. Stars, gas, and dust form only a small portion of the galaxy's true mass. The rest is this shadowy presence, binding it all together. The discovery of flat rotation curves transformed our perspective. It hinted that the universe was a far stranger and more mysterious place than we had imagined, with most of its matter hiding in plain sight, invisible to our eyes, yet profoundly influential on cosmic scales. Long before Vera Rubin's work made dark matter a mainstream concept, a handful of earlier astronomers had already caught glimpses of the cosmic invisibility cloak. Their discoveries in the 1930s were striking, but, for various reasons, were not widely heeded at the time. These were the forgotten clues, tantalizing hints of missing mass that came decades too early. In 1932, the Dutch astronomer Jan Oort studied the motions of stars in our Milky Way, specifically looking at how they move in the galaxy's local neighborhood. By measuring stars moving above and below the galactic plane near the Sun, he tried to calculate the total mass in this part of the galaxy. The mass he calculated turned out to be greater than what could be accounted for by all the visible stars and gas. In other words, even in our own galactic backyard, there seemed to be more gravity than visible matter could produce. Oort suggested that there might be unseen matter lurking in the Milky Way, perhaps faint stars, cold gas, or some other invisible material providing the extra pull. It was an extraordinary suggestion, but the data were limited, and the idea of invisible mass didn't take hold. Many assumed the discrepancy would vanish with better measurements, or could be explained by dim stars and nebulae that were hard to detect. Oort's hint of hidden matter remained an intriguing footnote, little discussed for years. Around the same time, across the ocean in California, another astronomer was grappling with an even larger scale mystery. Fritz Zwicky, a bold and eccentric Swiss-American astronomer, was studying clusters of galaxies, enormous systems where hundreds of galaxies swarm together, bound by gravity. He focused on the Coma cluster, a distant cluster of galaxies. By observing the Doppler shifts of the galaxy's light, Zwicky estimated their speeds as they moved within the cluster. They were moving surprisingly fast. In fact, they seemed to be moving too fast to be held together by the gravity of all the visible matter in the cluster, the stars in those galaxies. Zwicky then performed a simple calculation. He estimated the total mass needed to keep those fast-moving galaxies from flying apart. The number he arrived at was staggering. It was far, far greater than the mass of all the galaxy's stars that could be seen. To explain this, he proposed that the cluster contained a vast amount of unseen mass. He famously called it Dunkel Materie, German for dark matter. Fritz Zwicky, never one to shy away from bold ideas, pressed his case. He would tell anyone who would listen about the vast stuncle materia holding the coma cluster together. But in the 1930s, the idea was too radical for most. One can imagine him, armed with his calculations and a stubborn gleam in his eye, trying to convince colleagues that the universe was teeming with invisible mass. Many shrugged it off as an eccentric notion, not realizing that Zwicky had glimpsed a profound truth decades before it would be widely accepted. Zwicky's bold claim was that there was at least 10 times more invisible matter than visible matter in the coma cluster, acting like glue to hold the cluster together. This assertion, if true, meant the universe was fundamentally different from what most scientists assumed. However, his contemporaries met the idea with skepticism. The 1930s were a time when astronomy was just beginning to map the cosmos. The concept of entire clusters weighed down by invisible mass sounded almost fantastical. Moreover, Zwicky was known for his unconventional ideas and abrasive personality, which may have caused some colleagues to take his claims less seriously. For decades, Zwicky's dark matter evidence was largely ignored or forgotten, mentioned occasionally but not incorporated into mainstream science. It lingered as a curious anomaly, an outlier in the literature that few people knew what to do with. Yet, those early clues by Oort and Zwicky were real signposts on the road to discovery. In hindsight, we recognize that they had stumbled onto the shadowy truth. Something unseen was exerting gravitational forces on visible objects, from stars in the Milky Way to galaxies in a cluster. Their work was a precursor to the revolution that would come later. When Vera Rubin and others rediscovered the missing mass phenomenon in galaxies decades afterward, they were, in a sense, following the trail first blazed by these pioneers. The difference was that by the 1970s, technology and evidence had caught up to make the case incontrovertible. It's poignant to reflect that the universe had whispered its secret early on to those willing to listen. But sometimes, a discovery arrives before its time, and the world isn't ready to understand. The hints by Oort and Zwicky remained in the shadows until the rest of science caught up. Today, we honor their insight. They saw the invisible and gave it a name, even if it took many years for the idea of dark matter to truly take hold. Their forgotten clues, once ignored, now shine brightly as foundational evidence that helped shape our modern view of the cosmos. By the early 1980s, a profound realization was taking hold among astronomers and cosmologists. The evidence for hidden mass was no longer confined to one galaxy or one odd observation. It was popping up everywhere. Galaxy after galaxy showed the telltale signs of extra gravity with no visible source. Clusters of galaxies, too, clearly contained far more mass than could be seen in the form of stars. The whisperings from the quiet night sky had grown into an unavoidable statement. The universe, it appeared, was dominated by something other than the bright matter we know. This realization raised a pressing and slightly disconcerting question. Why couldn't the cosmos be explained by the matter we can see alone? If Newton's and Einstein's laws of gravity were correct, then every observation was telling us that an enormous amount of mass was simply missing from our view. By then, it was estimated that there might be at least 5 to 6 times more mass hiding in the dark than all the normal matter, stars, gas, planets, and people combined. Think about that. The brilliant galaxies, the glowing nebulae, the shining stars that fill our telescopes. These might be merely the tip of an immense cosmic iceberg. The bulk of the iceberg lies submerged in darkness, invisible yet exerting a very real influence. One line of evidence came from a phenomenon predicted by Einstein's theory: gravitational lensing. When light from a distant quasar or galaxy passes near a massive object on its way to us, the gravity of that mass can bend the light like a lens. In the 1980s and 1990s, astronomers began using gravitational lensing as a tool to map mass in galaxy clusters. They found instances where the light from background galaxies was being distorted and smeared into arcs and rings, indicating a huge amount of mass in the foreground cluster. Yet, when they counted up all the visible galaxies and hot gas in those clusters, it wasn't nearly enough to account for the lensing effect. The gravity bending the light had to include a large contribution from unseen mass. This was a striking confirmation. Even the way light traveled through the cosmos was telling us of massive invisible structures lurking in space. Moreover, computer simulations of the growth of cosmic structures suggested that without a dominant component of dark matter, we couldn't explain how the universe evolved from the smooth spread of matter after the Big Bang to the lumpy web of galaxies and clusters we see today. Ordinary matter, which interacts with light and gas, would have taken too long to clump into galaxies on its own. But if there was a hefty amount of dark matter providing gravitational scaffolding, structure could form much more quickly and match the large-scale patterns observed in the universe. This theoretical evidence lined up neatly with the astronomical observations, painting a consistent picture. Visible matter alone simply wasn't sufficient to build the cosmos we inhabit. By this point, the question was no longer if dark matter existed, but rather what it was. The cosmos had forced our hand. We had to accept that some new kind of mass was out there. The focus began to shift from convincing ourselves that dark matter was real, that battle was largely won by the weight of evidence, to uncovering the nature of this mysterious substance. Was it made of some exotic particle? Was it perhaps ordinary matter in unusual forms, like clouds of cold gas or faint, dead stars that had escaped detection? Or, as a few stubborn skeptics wondered, could it be that our theory of gravity needed revision instead? The stage was set for a new kind of inquiry. Scientists were poised to go beyond merely observing the effects of dark matter. Now they wanted to pinpoint exactly what this elusive majority of the universe is. The next step in our journey was to delve into the nature of dark matter itself, an exploration that would require creativity, new technology, and an openness to surprises. The universe had presented us with a haunting truth. The darkness between the stars was not empty at all, but full of something fundamental and unknown. With evidence in hand from every scale, galaxies, clusters, the path of light, and the echo of the Big Bang, the need for dark matter became one of the central questions of modern astronomy and physics. The cosmic stage was set for unveiling the true identity of this hidden mass. The story was about to shift from why dark matter must exist to the compelling quest to discover what it actually is. So, what could this dark matter be? With the need for an invisible mass now clear, scientists around the world turned to the task of identifying it. At first, many wondered if dark matter might not be something exotic at all, but simply ordinary matter hiding in hard-to-see forms. Perhaps the universe was full of dim, burned-out stars, wandering planets, or black holes that emit little to no light. These would be made of the same kind of atoms as everything else, just shrouded in darkness. Astronomers called such possibilities MACHOS, short for Massive Astrophysical Compact Halo Objects, essentially big clumps of normal matter like faint stars or primordial black holes roaming the outskirts of galaxies. Throughout the 1990s, teams of researchers set up clever studies to search for these dark objects, often by looking for slight gravitational blinks of starlight. For instance, if an unseen object passed in front of a distant star, its gravity would bend and magnify the star's light, causing the star to momentarily brighten as seen from Earth. By monitoring millions of stars in neighboring galaxies like the Magellanic Clouds, Astronomers hoped to catch these brief brightenings that would reveal the presence of otherwise invisible massive objects. They did find a few such events, evidence of some lonely brown dwarfs, and perhaps the occasional small black hole drifting in galactic halos, but not nearly enough to account for the vast amount of missing mass. One by one, the simple, dark, hiding normal matter ideas were ruled out or heavily constrained. It seemed that dark matter wasn't simply a collection of hidden, ordinary stars or black holes. The bulk of it had to be something else. Another idea was to consider particles we already knew about that are invisible. Neutrinos. Neutrinos are ghostly subatomic particles produced in nuclear reactions, like those in the sun or in exploding stars, that hardly ever interact with normal matter. Trillions of them pass through your body each second without a trace, and you never notice. In the late 20th century, scientists discovered that neutrinos actually have a tiny bit of mass, contrary to earlier assumptions that they were massless. Could swarms of neutrinos be the dark matter? For a time, it was a tantalizing thought. Neutrinos are dark and extremely abundant, but calculations showed that neutrinos, being very light and moving at nearly the speed of light, would not stay bound in the small clumps needed to form galaxies and clusters. They would stream out of galaxies rather than lingering and adding to the gravitational glue. Moreover, the total mass neutrinos contribute, while not zero, turned out to be far too little to explain dark matter fully. Thus, the idea of dark matter consisting of fast, hot particles, like neutrinos, fell out of favor. Neutrinos could only be a small part of the story, not the main answer to the missing mass problem. These early investigations, by failing to turn up a simple answer, cleared the path toward a profound realization. Dark matter likely wasn't made of any familiar substance at all. If it were normal atoms in any form, stars, planets, gas, dust, we would have seen some trace of it by now, whether through faint light, heat, or the blocking of background light. Even clouds of cold gas would absorb starlight passing through them. Dust would glow in infrared. Black holes might betray themselves through X-ray flares as they swallow surrounding matter. But the dark matter offered no such clues to telescopes. It seemed truly dark in every sense, not emitting light, not casting detectable shadows, and not interacting much with ordinary matter except through gravity. This pointed scientists toward new hypotheses. Perhaps dark matter was a new kind of elementary particle, something not yet seen in our laboratories. In other words, an entirely different ingredient of the universe was at play, one that doesn't appear on the periodic table of elements. It had to be something beyond the ordinary building blocks that we have known, a component of the cosmos that had managed to elude direct detection so far. One leading hypothesis for this new particle was the idea of a WIMP, a whimsically named, weakly interacting massive particle. The name tells the story. If dark matter were made of heavy particles that interact only very feebly, via the weak nuclear force and gravity, but not with light, they would be essentially invisible and ghost-like. Such particles could drift through the Earth without anyone noticing, only very rarely colliding with ordinary atoms. Yet if enough of them were around, their collective gravity could form galaxies and hold clusters together, matching all the observations of dark matter's effects. Theoretical physicists found WIMP-like particles appealing because some extensions of physics beyond the standard model, like a theory known as supersymmetry, naturally predicted heavy, stable particles that would have exactly the needed properties of dark matter. One example is a hypothetical particle often nicknamed the neutralino, a heavy, electrically neutral cousin of the neutrino. Intriguingly, calculations suggested that a particle weighing on the order of 100 times the mass of a proton, interacting through the weak force, would have been produced in the right amount in the hot early universe to leave about the abundance of dark matter we detect today. This coincidence was sometimes playfully referred to as the WIMP miracle, the notion that the physics of the early universe might naturally yield the correct abundance of such particles. For a while, WIMPs were the star candidate. They fit the bill: massive enough, abundant enough, and dim and inert enough not to have been noticed yet in our experiments. It seemed like a matter of time before we would either detect a WIMP directly or create one in a collider, confirming dark matter's identity. Another compelling candidate was something much smaller and more peculiar: the axion. Axions were originally proposed to solve a completely different problem in physics related to the strong force inside atomic nuclei. But it turned out that if axions exist, they could also be excellent dark matter particles. Axions would be extremely light, far lighter than even electrons, and they interact with matter so weakly that they have never been seen. Yet they could be very numerous, and under the right conditions, they would behave collectively like a cold, pressureless fluid permeating space, just what dark matter needs in order to help form galaxies early and hold galaxy clusters together. Unlike WIMPs, which are heavy and relatively rare particles, axions would be ultralight but astronomically plentiful. Both WIMPs and axions shared a crucial feature: they don't shine or absorb light, and they pass through normal matter without a fuss, making them dark matter candidates that fit the bill. With these candidates in mind, the hunt was on. Scientists built sophisticated experiments to try to catch a glimpse of these elusive particles. In deep underground laboratories, shielded by layers of rock from the clamor of cosmic rays, giant detectors have been deployed to wait patiently for a rare interaction. For WIMPs, detectors often use ultra-pure crystals or large tanks of liquefied noble gases such as xenon. The idea is that on the exceedingly rare occasion a WIMP particle smacks into an atom in the detector, it will make that atom recoil or produce a tiny flash of light or a faint electric signal that can be picked up. Some of these detectors sit in old mine caverns a mile underground, or in laboratories beneath mountains, where day and night scientists maintain a vigilant watch. It's a bit like sitting in a sealed, silent room, ears straining for the slightest pin drop. These experiments are essentially eavesdropping on the universe, hoping to hear the softest whisper of a particle that hardly ever speaks. Year after year, the detectors have been listening, and so far, each time, they have reported only silence. In that subterranean laboratory, perhaps in the still hours of the night, a physicist might glance at a monitor showing a flat line of data. No signals, just the quiet hiss of background noise. It could be discouraging, but instead, it instills resolve. They double-check the equipment, ensure everything is in perfect order, and remind themselves that even one tiny flash of light on that screen someday could herald a monumental discovery. The patience in these dark matter hunts is immense. Years may pass without a whisper, yet the scientists continue the vigil, driven by the possibility that tomorrow or the next day, the silence might break and reveal a new chapter of physics. Meanwhile, other experiments have been set up to hunt for axions. These often involve extremely strong magnetic fields and finely tuned microwave cavities. In essence, trying to encourage any axions floating through to convert into a faint electromagnetic signal. The setup is a bit like a radio receiver, tuned carefully to the frequency an axion signal might appear at. Scientists slowly scan through frequencies, listening for a telltale tone or slight excess of photons that could indicate axions shifting into detectable light. It's an incredibly delicate search, akin to trying to hear a single specific note played softly in a distant symphony. As of now, axions remain hypothetical. No definitive whisper from them has been heard yet. But the searches continue, growing more sensitive each year, inching through the dial of nature's hidden frequencies. Physicists have also enlisted powerful particle accelerators in the quest. The Large Hadron Collider, LHC, in Geneva, the most energetic collider in the world, smashes protons together at near light speed. In those collisions, energy can transform into matter. Einstein's E equals mc squared in action. If dark matter particles can be created, an experiment like the LHC might produce them. The catch is that dark matter particles would slip through the detectors unnoticed. They interact so weakly that they leave no direct trace, like ghosts passing through a wall. So physicists must look for indirect clues. They meticulously account for all the energy and momentum in the debris of each proton collision. If some energy appears to be missing, as if something invisible carried it away, it could be a sign that dark matter was produced and escaped. It's a bit like hearing an off-key silence in a loud orchestra, noticing that something expected is absent. So far, despite the immense power of the LHC and other colliders, no clear missing energy signal attributable to dark matter has been observed. But the search is young, and each new run of the collider probes deeper into the unknown, leaving open the possibility that an unexpected discovery may yet emerge. All these non-detections might sound discouraging, but in science, sometimes knowing what something is not is a step toward knowing what it is. Each experiment that fails to find dark matter squeezes the theoretical possibilities, guiding researchers to refine their ideas about what dark matter could be. In a way, the dark matter puzzle has challenged physicists to become more creative and more precise. The search continues with ever-improving sensitivity. New detectors are being built that are larger, quieter, and more tuned to the faintest signals. Future colliders are envisioned to reach even higher energies. The hunt is intensifying, and dark matter remains one of the biggest open questions in physics, keeping generations of scientists intrigued and motivated. It is almost as if dark matter is playing a cosmic game of hide and seek, always one step beyond our grasp. But each attempt we make brings us a little closer, whittling down where that elusive answer could be. While laboratory searches proceed, the universe itself continues to offer clues about dark matter's nature. One remarkable observation came from a cosmic accident: the collision of two galaxy clusters, an event famously known as the Bullet Cluster. In this colossal smash-up, observed in 2006, telescopes saw that the hot gas from the two clusters, which makes up most of the normal matter and shines in X-rays, crashed into each other and slowed down, piling up near the center of the impact. But the majority of the mass, deduced by mapping the gravitational lensing distortions of background galaxies, simply passed through the collision unhindered and kept going with the individual clusters. In the Bullet Cluster, the sources of gravity ended up separated from the sources of ordinary matter, the glowing gas and visible galaxies. This is exactly what you'd expect if most of the cluster's mass is in the form of collisionless dark matter that doesn't interact with gas or stars except by gravity. It was a stunning visual confirmation that whatever dark matter is, it behaves very differently from normal matter. Where normal matter collides, heats up, and sticks, like two clouds of gas merging, dark matter just glides through, its presence revealed only by the gravity it leaves behind. Even on scales far larger than galaxy clusters, dark matter has arranged itself into a vast cosmic web. Astronomers using computer simulations and deep sky surveys have found that galaxies are not scattered randomly through space, but are aligned along enormous filaments and tendrils of unseen matter. This lattice of dark matter filaments stretches for hundreds of millions of light years, and galaxies form like sparkling dewdrops along these invisible threads. Where multiple filaments meet, they create the dense knots where clusters of galaxies gather. In effect, dark matter provides the architecture of the universe on the grandest scales. It is the scaffolding on which the visible matter collects. Without it, the universe would look vastly different, likely a more uniform, diffuse spread of matter, lacking the rich tapestry of galaxies and galaxy clusters we observe. The cosmic web is a spectacular testament to dark matter's role, an unseen framework spanning the cosmos that guides the formation of all the structures we see in the sky. Observations like these allow scientists to infer some of dark matter's key properties. We know it doesn't clump into small objects in the way ordinary matter does. Instead, it forms large, diffuse halos around galaxies. We know it interacts very weakly, if at all, with forces other than gravity. It doesn't emit light or heat, it doesn't feel the electromagnetic force, and it doesn't stick together via the strong nuclear force. If it did any of those things, we would have detected it by now in laboratory experiments or astrophysical observations. We also know it must be relatively slow-moving, what physicists call cold, when structures form. Otherwise, galaxies and clusters as we see them would not have coalesced so early in cosmic history. Piece by piece, these clues constrain the nature of dark matter. It's cold, it's effectively invisible, or dark, and non-interactive. It's not made of the usual protons and neutrons at all, what scientists term non-baryonic, and it is amazingly abundant. In fact, from measurements of the cosmic microwave background, the faint afterglow of the Big Bang, and other cosmological data, we can even quantify how much dark matter exists. About 85% of all the matter in the universe is dark matter, leaving only about 15% as the ordinary matter that makes up the stars, planets, and living beings. Put another way, if you imagine all the matter in the universe as a pie, only a small slice of that pie is composed of familiar atoms. The rest is this unseen mass. Dark matter isn't just the dominant mass in galaxies far away. It dominates right here in our own cosmic neighborhood too. It's humbling to realize that we have more detailed maps of where dark matter lies across billions of light years than we have understanding of the dark matter particles drifting right here around us. We live within the Milky Way's dark matter halo, a vast, invisible sphere of mass in which our solar system is embedded like a tiny pearl in a hidden sea. Right here on Earth, billions of dark matter particles may be flowing through your room and your body each moment, like a gentle, ghostly wind. We don't see it or feel it, but it's there, as pervasive as the air we breathe, yet far more mysterious and undetectable to our senses. We move through this unseen ocean of dark matter as the sun orbits the center of the galaxy, immersed in a substance that, so far, we only know by its gravitational whispers. The story of dark matter is one of both revelation and ongoing mystery. In the last century, we have realized that dark matter's overwhelming presence shapes the cosmos at every level. We've mapped its distribution and understood its vital role as the universe's hidden scaffolding. It truly is the hidden skeleton of the universe, an invisible framework that holds the visible world together. And yet, the true nature of that skeleton remains unknown. The darkness that once simply symbolized ignorance has become a frontier of active exploration. This realization has fundamentally changed our perspective. We now understand that the vast majority of matter in the universe is something we have yet to identify. It's a humbling insight, reminding us that even in the darkness, there are truths waiting to be discovered. The pursuit of dark matter's identity is a testament to human curiosity and wonder, a grand quest to illuminate the unseen. As researchers press on, They carry with them the hope that one day we will finally understand what dark matter is, and that knowledge will open a new chapter in our understanding of reality. In the stillness of a clear night, as you gaze up, you might take comfort in the stars that shine. But remember also the darkness between those stars, the soft black canvas upon which the cosmos is drawn. That darkness is filled with the majority of matter in the universe, patiently holding galaxies together and guiding their paths. We don't yet know what forms the essence of that darkness, what strange particle or substance makes up the dark matter. But we do know it's out there, embracing the cosmos in its invisible grip. The next time you feel the night's quiet, think of the profound secret it carries. In that tranquil darkness lies the hidden scaffolding of reality itself. We are only just beginning to understand this cosmic shadow, and the pursuit of its truth is a testament to human curiosity and wonder. The journey to uncover dark matter's identity continues, quietly, persistently. Each day, deep underground or high in the mountains, detectors wait in silence. Each night, telescopes probe the sky, mapping the unseen. Little by little, the universe is giving up its secrets. Someday, perhaps when we least expect it, a tiny glimmer of a signal will reveal the nature of dark matter, and a new chapter of understanding will begin. Until then, under the quiet night sky, we live side by side with an invisible cosmic companion, a reminder that not all that is real can be seen, and not all that is dark is empty. In this way, darkness has taught us more about the universe than we ever imagined, and it invites us onward to keep exploring the beautiful mystery of the unseen. For years, the notion of an invisible mass haunting the galaxies hung at the fringes of astronomy. Under the vast night sky, it was a speculative whisper, a hypothesis waiting for proof. Many astronomers remained skeptical, demanding more than just hints of this ghostly presence. Then, on a clear desert night, an astronomer named Vera Rubin quietly began to turn that whisper into a resounding truth. In the late 1960s, Vera Rubin found herself at the Kitt Peak Observatory in Arizona, peering intently at the Andromeda Galaxy through a powerful telescope. High above the Sonoran Desert, the air was still and clear, perfect conditions for stargazing. Rubin was no stranger to defying expectations. She was a woman in a field then dominated by men, persistent and passionate about uncovering the cosmos's secrets. Together with her colleague Kent Ford, she set out to measure the speeds of stars orbiting the galaxy's center with unprecedented precision. They used a new spectrograph technology to split the starlight into its component colors and capture the slight shifts in wavelength, Doppler shifts, that reveal how fast those stars are moving toward or away from us. Rubin expected that the stars farther from the galaxy's center would orbit more slowly, their light showing only gentle shifts due to more leisurely motion. After all, this would mirror the familiar pattern of our own solar system, where distant planets circle the sun more slowly than those closer in. They used the new spectrograph technology to split the starlight into its colors and capture the slight shifts in wavelength, Doppler shifts, that reveal how fast those stars are moving. Rubin expected that the stars farther from the galaxy's center would orbit more slowly, their light showing only gentle shifts due to more leisurely motion. After all, this would mirror the familiar pattern of our own solar system, where distant planets circle the sun more slowly than those closer in. But as the data accumulated, Rubin's astonishment grew. By the end of the first night's observations, something unexpected was emerging in the numbers. The stars at the outer edges of Andromeda were whipping around just as fast as the stars near the galaxy's bright core. Plotting the rotation curve, a graph of orbital speed versus distance from the center, she saw it flatten out instead of plunging downward. In other words, the outer stars were moving far too quickly for the galaxy's visible mass to hold them in orbit. At such speeds, they should have been flung outward into the darkness of intergalactic space, escaping the galaxy's gravitational pull altogether. Yet there they were, circling calmly, as if held by an unseen tether. Rubin double-checked the results, wondering if an error or an overlooked source of mass could explain it. But observation after observation confirmed the puzzling trend. The surprises came very quickly, Rubin recalled years later. By the end of the first night, we were puzzled by the shape of the rotation curve. Her experimental precision and cautious approach left little room for doubt. Something significant was missing from our accounting of mass in the galaxy. Rubin realized that the visible matter, the shining stars and glowing gas clouds we can see, was not nearly enough to keep those fast-moving outer stars bound to the galaxy. The galaxy simply didn't weigh enough, based on its starlight, to account for the tight grip on those stars speeding along the outskirts. There had to be much more mass present than anyone could see, enveloping the galaxy like an enormous, invisible halo. It was as though Andromeda, and by extension many other galaxies, were cocooned in a vast sphere of hidden matter. This missing mass, Rubin concluded, was what earlier astronomers had only hypothesized about: dark matter. Night after night, Rubin and Ford extended their observations to other spiral galaxies, large and small, nearby and distant. With meticulous care and patience, she mapped the rotation speeds of stars and gas orbiting at various distances from each galaxy's center. Again and again, the pattern repeated itself. No matter how faint or how majestic the galaxy, the stars far from the center were moving at astonishing speeds that should have torn them away if only visible matter were present. Even the smallest galaxies showed signs of this hidden mass. For example, tiny dwarf galaxies orbiting the Milky Way, objects with only a few million stars, compared to the Milky Way's hundreds of billions, appear to be held together predominantly by dark matter. In these puny systems, the stars move under the grip of a halo of invisible matter, demonstrating that dark matter's influence permeates galaxies of all sizes. The rotation curves for these galaxies did not drop off as one moved outward. Instead, they stayed flat or even rose slightly. It was a cosmic mystery etched clearly in the data. In galaxy after galaxy, Rubin found an extraordinary amount of matter missing, at least missing from sight, yet clearly there in mass. These results were more than just points on a graph. They were a turning point in astrophysics. In the quiet, late hours of those observing sessions, Vera Rubin had gathered evidence that would revolutionize our understanding of the cosmos. The idea of dark matter was no longer a mere curiosity or a speculative notion on the fringes of astronomy. It was now something real and unavoidable, demanded by the motions of stars themselves. Rubin's work showed that something unseen dominated the mass of galaxies. In fact, her measurements implied that galaxies are mostly made of this invisible matter, far outweighing all the stars, gas, and dust that give off light. When Rubin began presenting her findings to the astronomical community in the 1970s, the reaction was a mix of intrigue and healthy skepticism. Could it really be true that an invisible substance outweighs the luminous matter in galaxies by a factor of 5 or more? The notion challenged the comfortable assumption that we understood what the universe is made of. But Rubin had built a strong case, and her careful methodology and clear data were difficult to dismiss. Other astronomers soon followed up on her work, observing even more galaxies and extending studies to different galaxy types. One by one, their results confirmed Rubin's conclusions. By the early 1980s, The evidence had become overwhelming. The universe, it appeared, was filled with dark matter, an as yet unidentified form of mass that neither emits nor absorbs light, but whose gravity is felt on cosmic scales. Vera Rubin's discovery transformed dark matter from an obscure hypothesis into a central pillar of modern cosmology. It also cemented her legacy as one of the great astronomers of the 20th century. Her perseverance and insight had pulled the curtain back on a cosmic secret. It's worth noting that Rubin achieved this breakthrough at a time when women in astronomy faced many barriers. She herself was often the only woman in observatories and conferences. Yet she pressed on with quiet determination. At Palomar Observatory, where she was the first woman officially allowed to observe, she famously pasted a paper cutout of a skirt on the door of the all-male restroom, a gentle, sly act of defiance that symbolized breaking barriers. Rubin's success was not just scientific, but also inspirational, opening doors for others who had been marginalized. By illuminating the presence of dark matter, Rubin fundamentally changed our picture of the universe. We now understand that the glittering spiral arms of a galaxy are only the tip of the cosmic iceberg. Encircling each galaxy, extending well beyond the furthest visible stars, is a massive halo of dark matter that provides the gravitational glue to hold everything together. If dark matter were somehow visible to our eyes, we would see that each spiral galaxy's luminous disk is nestled inside an enormous diffuse halo, perhaps 10 times wider than the galaxy's bright starlight extent. The galaxy's appearance would be like a tiny firefly floating in a vast, transparent cloud of matter. Because of Rubin's work, astronomers came to accept that what we can see, all the stars and glowing gas, is only a small fraction of what truly exists. In the decades that followed, dark matter went from a radical idea to a cornerstone of cosmological theory, shaping every new model of how galaxies form and evolve. Fittingly, Vera Rubin lived to see her once controversial findings become scientific consensus, though the ultimate nature of dark matter remained elusive in her lifetime. She often expressed delight and curiosity rather than frustration at this mystery. Her humility and sense of wonder endured. She liked to remind people that we still know less about the universe than we pretend. Today, her legacy continues. A new state-of-the-art telescope in Chile, the Vera C. Rubin Observatory, has been named in her honor and will carry forward the quest to map the sky and uncover more cosmic mysteries, including the behavior of dark matter on the largest scales. The revelation from galactic rotation curves marked a new era. Astronomers now had to reckon with the fact that everything we see, every shimmering star, every glowing nebula, every cluster of brilliant galaxies, is only a small fraction of what is truly there. The rest, the majority of matter, is dark. This profound shift in perspective opened up deeper questions. If dark matter is real and everywhere, where else can we find its influence? What other cosmic phenomena, once perplexing, might be explained by this hidden mass? As Rubin's work sank in, scientists began to revisit earlier observations and long-standing cosmic puzzles with fresh eyes. They started to ask with renewed interest, could dark matter also explain other enigmas that had been observed but not understood? Decades before Rubin's groundbreaking work, one such cosmic puzzle had already been observed and largely overlooked. In the early 1930s, a Swiss-American astronomer named Fritz Zwicky trained his telescope on a far-off grouping of galaxies known as the Coma Cluster. This cluster, located in the direction of the constellation Coma Berenices, is an enormous swarm of galaxies bound together by gravity, roughly 300 million light-years from Earth. Through the eyepiece, Zwicky would have seen faint smudges of light scattered across the darkness, individual galaxies teeming with stars, yet appearing as small, nebulous patches from our distant vantage point. The Coma cluster contains thousands of galaxies, all together in a giant gravitational dance. Zwicky set out to measure the speeds at which those galaxies move within the cluster, using their Doppler shifts, the slight changes in their light due to motion, as his guide. He was applying a bit of cosmic bookkeeping. By measuring how fast the galaxies were buzzing around, he could infer how much gravity, and thus how much mass, was needed to keep them from flying off into space. The results of Zwicky's measurements were startling. The galaxies in the Coma cluster were zipping around at such high velocities that, according to the known laws of gravity, the cluster should have blown itself apart. In a system held together by gravity, the faster the components move, the more mass is required to hold them in orbit. Zwicky calculated how much mass the cluster would need to keep those fast-moving galaxies from escaping its grasp. The number he arrived at was mind-boggling. It was far, far higher than the mass one could account for by adding up all the light from the cluster's galaxies. In fact, depending on the assumptions, it seemed the Coma cluster had perhaps 50 or more times the mass that was visible. Zwicky realized that there must be a tremendous amount of unseen matter in the cluster acting as glue. With bold confidence, he proposed that this invisible mass was real and provided the gravitational heft needed to bind the cluster. He famously dubbed this mysterious material Dunkel Materia, German for dark matter. This was one of the first times in modern astronomy that someone explicitly suggested the existence of a vast amount of unseen matter in the universe. Interestingly, around that same time, Dutch astronomer Jan Oort found hints of missing mass in our own Milky Way. In 1932, he observed that stars in the outskirts of our galaxy were moving faster than expected, implying unseen matter in the galactic halo. Like Zwicky's idea, Oort's evidence was largely overlooked then. Zwicky's insight was ahead of its time. He imagined an invisible glue permeating the cluster, holding the galaxies together. However, in the 1930s, the idea was simply too radical for most of the scientific community to accept. Astronomy was still reveling in recent discoveries. Galaxies had only recently been recognized as distant island universes, and the expansion of the universe had just been discovered. The notion that these new cosmic structures might be mostly made of something invisible was a step too far for many. Colleagues reacted to Zwicky's findings with skepticism. Some believed he must have mismeasured the galaxy speeds or underestimated the light from faint galaxies. Others thought there might be large quantities of dim stars or gas in the cluster that his telescope couldn't detect, which could account for the extra mass without invoking exotic invisible matter. Moreover, Zwicky himself was a flamboyant, sometimes abrasive character, known for unconventional ideas, which may have made his peers less inclined to take this wild concept seriously. Lacking broader evidence, Zwicky's dark matter finding was largely set aside and soon faded into obscurity. For decades, textbooks and astronomers paid little heed to the missing mass of the Coma cluster. The term dark matter appeared in a few discussions here and there, but it did not gain traction. It lingered as a historical footnote, a curious anomaly noted by a maverick astronomer awaiting rediscovery. That rediscovery came thanks to Vera Rubin and the galaxy rotation curves. After Rubin's work in the 1970s, provided solid evidence that individual galaxies are filled with dark matter, the astronomical community began to revisit Zwicky's observations with new appreciation. If every galaxy contains a dark matter halo, then a cluster of galaxies like Coma should indeed have not just the sum of all those halos, but possibly additional dark matter binding the cluster as a whole. Astronomers in the late 1970s and 1980s started to systematically measure the masses of many galaxy clusters using improved telescopes and techniques. Time and again, they found the same discrepancies Zwicky had reported. Clusters contained far more mass than could be seen. The galaxies within clusters were moving too fast for the visible mass alone to hold them together. It wasn't just the Coma cluster. It was virtually every cluster studied. The once ignored missing mass problem re-emerged as a major issue in cosmology, now supported by a growing body of evidence. Further observations provided even more clarity. In the 1970s, astronomers began detecting X-rays coming from galaxy clusters, and they discovered vast clouds of hot gas permeating these clusters. This gas, heated to tens of millions of degrees, fills the space between galaxies in a cluster and is actually far more massive than all the stars in the galaxies combined. The gas itself is invisible to optical telescopes, but X-ray observatories revealed its presence. Including the mass of this hot gas helped. Clusters turned out to have much more normal matter than just the stars in galaxies. But even with gas accounted for, the total visible mass, gas plus stars, still fell drastically short of what was needed to explain the gravitational grip of clusters. For example, in a typical rich cluster, the galaxies might contribute only a few percent of the total mass, the hot gas perhaps 10 to 20%, and the rest, the lion's share, must be dark matter. In essence, the bulk of cluster matter was still missing unless one included dark matter in the tally. By the 1980s, astronomers had embraced the reality that Zwicky's invisible glue was no fantasy. It was an essential component of the universe. The Coma cluster and other clusters were recognized to be enveloped in enormous dark matter halos, just as individual galaxies are. Fritz Zwicky, long after his time, was vindicated. His early use of the term dark matter gained new life, and today it's the common name for this mysterious substance. One can imagine a bit of cosmic irony. The very idea that had been dismissed in his day turned out to be a cornerstone of our modern understanding of the cosmos. Fritz Zwicky, once considered an eccentric, is now hailed as a pioneer who glimpsed the truth of dark matter well before his peers. His Dunkel Materia insight, decades ahead of its time, stands as a testament to how the universe occasionally whispers its secrets to those bold enough to listen. Now, with dark matter accepted as the invisible backbone holding galaxies and clusters together, scientists pressed on to find new ways of detecting and mapping this elusive mass. If dark matter cannot be seen directly by its light, perhaps nature offers other means to reveal its presence. One of those ways comes from an effect predicted by Einstein's theory of gravity, an effect that bends light itself. Through this phenomenon, astronomers found they could literally observe the footprint of dark matter in the distortion of distant starlight. This phenomenon, known as gravitational lensing, had been anticipated long before by Albert Einstein's theory of general relativity. According to Einstein's revolutionary ideas, mass can warp the fabric of space itself, causing light to travel along curved paths. In effect, gravity can act like a lens, bending and focusing the light from distant objects. For a time, this effect was known only as a theoretical prediction. There were early hints and subtle confirmations. For example, in 1919, during a famous solar eclipse expedition, astronomers observed that stars appearing near the eclipsed sun's edge were slightly displaced from their normal positions. Their starlight, bent by the sun's gravity, exactly as Einstein had foretold. But such tests were small scale, and the bending was tiny. As telescopes grew more powerful, and our gaze turned to the deep cosmos, astronomers began to witness spectacular examples of gravitational lensing on a much larger scale. And with those observations, they found a new way to see the invisible mass in the universe. One of the first dramatic cosmic lensing discoveries came in 1979. A distant quasar, a super-bright galaxy nucleus, was found to have a twin. Two identical images of the same quasar appeared side by side in the sky. This puzzling sight turned out to be a single quasar directly behind a massive foreground galaxy, whose gravity was splitting the quasar's light into two paths, sending two images of that quasar to Earth. It was a striking confirmation. Gravity was not only bending light, but in this case, producing a cosmic illusion, duplicating a distant beacon. Since then, astronomers have found many more examples of gravitational lensing, some with multiple images of a single background galaxy or quasar, and some where the light is stretched into long arcs or smeared shapes. Imagine a distant galaxy, far beyond our own, shining with the combined light of billions of stars. Now imagine that along our line of sight to that remote galaxy lies a massive cluster of galaxies much closer to us. The immense gravity of that intervening cluster warps space like a heavy weight on a trampoline. As the light from the faraway galaxy passes by the cluster, it doesn't move in a straight line. Instead, it flows along the curved space, redirected and refocused. By the time the light reaches Earth's telescopes, the distant galaxy's image is no longer a neat point. It may appear stretched into an arc of light, or even split into multiple patches around the edges of the cluster. To our eyes, it can look like a celestial mirage, the background galaxy smeared and duplicated by the cluster's gravitational field, creating those ghostly rings or arcs of light. In rare cases of almost perfect alignment, the distant galaxy's light can be bent into a complete circle around the intervening object, an eerie halo known as an Einstein ring. These beautiful distortions are more than curiosities. They are precise messengers of gravity and thus tools for measuring mass. Astronomers can analyze the shapes and positions of the arcs, rings, or multiple images to calculate how much mass must be present in the intervening cluster or galaxy to bend the light in that specific way. Time and again, such studies have revealed that the visible matter, the stars in the cluster's galaxies, and even the hot gas spread throughout the cluster, accounts for only a small fraction of the total mass required. The rest of the mass causing the light's distortion is invisible. In other words, gravitational lensing provides direct evidence for dark matter. It's as if the dark matter, though unseen itself, casts a kind of shadow by the way it warps the light from objects behind it. By carefully mapping these distorted images, astronomers can chart the distribution of mass within the lensing cluster, effectively sketching out the clumps and halos of dark matter that would otherwise remain hidden. One particularly dramatic case of gravitational lensing offered a kind of smoking gun for dark matter's reality. Astronomers call it the bullet cluster, the name given to two galaxy clusters that collided with each other in a tremendous cosmic crash. When these two giant clusters ran into one another, the individual galaxies, which are relatively small targets separated by vast distances, mostly flew past each other without direct collisions, and the enormous dark matter halos of each cluster interpenetrated freely. However, the clusters were also filled with hot, X-ray emitting gas, which constitutes the bulk of the ordinary matter in them. That gas from one cluster slammed into the gas from the other, creating a shockwave and slowing down, like two clouds of smoke colliding and dragging on each other. In the aftermath of this collision, telescopes observed that the great clouds of hot gas had been left behind towards the center of the impact zone, stripped away from many of the galaxies. Yet, when astronomers used gravitational lensing to map where the mass was, they found it mostly aligned with the galaxies that had moved on ahead. The majority of each cluster's mass was not where the ordinary matter, gas, had piled up. It was where the galaxies, and presumably the dark matter, had travelled through. In images of the bullet cluster, one can see two distinct components highlighted. The pink glow of normal matter, the hot gas, lingering in one place, and a separated blue-coloured overlay, a reconstruction from lensing data, indicating where the mass lies. Those blue areas mark where gravity is strongest, essentially showing the location of the dark matter. This observation is profoundly important. It demonstrates that dark matter exists separately from ordinary matter. In the bullet cluster, the dark matter kept moving straight through the collision, while the normal matter got bogged down and left behind. To many scientists, this became one of the clearest affirmations that an unseen form of matter is truly there, because no modification of the laws of gravity alone could easily explain such a separation of mass and light. Astronomers have since observed other cluster collisions that echo the bullet cluster's telltale pattern of separation between normal and dark matter, further bolstering the case that dark matter is a real, physical ingredient of the cosmos. Beyond such rare, dramatic events, gravitational lensing has become a routine but powerful tool to map dark matter across the universe. Often the lensing effects are subtle. There might not be giant luminous arcs obvious to the eye, but the shapes of background galaxies are minutely warped as their light passes through the gravitational fields of intervening structures. By studying these tiny distortions across wide swaths of sky, scientists can detect the gentle signature of dark matter clumps, even outside of big clusters. This technique is sometimes called weak lensing, since the bending of light is slight. Yet with statistical analysis of many background galaxies, the presence of dark matter can be inferred. Using such methods, researchers have created detailed mass maps showing where unseen matter congregates. For instance, surveys using the Hubble Space Telescope have traced the dark matter in and around numerous galaxy clusters, revealing that the invisible mass forms dense knots in cluster cores and extends far beyond the visible galaxies. Encouragingly, these mass maps from lensing align with what we expect from other evidence. They confirm that massive dark matter halos envelop clusters and even connect between clusters in web-like strands. Gravitational lensing also serves as a natural telescope. The same warping of space that reveals dark matter's presence can magnify and brighten the light of far background objects. Taking advantage of this, astronomers have observed galaxies from the universe's early epochs that would normally be too faint to see, by using massive clusters as cosmic lenses that boost and focus the distant light. In this way, the unseen mass not only shapes the cosmos, but also helps illuminate it, acting as a gravitational magnifying glass that lets us peer further into space and time. With sufficient evidence in hand to support dark matter's existence, scientists are now taking gravitational lensing a step further, using it not just to detect dark matter, but to chart its grand structure throughout the cosmos. Ambitious new surveys are underway and in planning. The Vera C. Rubin Observatory, for example, will photograph vast areas of the sky with exquisite sensitivity, capturing shapes of billions of distant galaxies. Hidden in those shapes are lensing signals from intervening dark matter, which will allow researchers to map large-scale distributions of dark matter like never before. Likewise, space missions such as NASA's upcoming Nancy Grace Roman Space Telescope are designed to measure weak lensing across cosmic history, helping to create a 3D map of where dark matter lies from the present day back to earlier epochs. Through these efforts, gravitational lensing is letting us peel back the curtain on the invisible. We are beginning to see the universe's dark scaffolding come into view. Through the lens of gravity, all the earlier clues from rotation curves and cluster dynamics gain a visually compelling confirmation. We can actually witness the imprint of dark matter bending the light of galaxies billions of light years away. This method of seeing the unseen strongly reinforces what Vera Rubin and Fritz Zwicky had inferred in other ways. And remarkably, evidence for dark matter's influence doesn't only come from the present-day universe or from light and gravity at work today. Clues are also encoded in something even more ancient and subtle: the very afterglow of the Big Bang, still faintly illuminating the universe. In that primordial light, the cosmic microwave background, scientists have found a fingerprint of dark matter dating back to the dawn of the cosmos. Long before galaxies and clusters ever existed, the universe itself was a much smaller, hotter, and denser place. To truly appreciate dark matter's role, we must journey back to this early epoch and read the clues written in the oldest light we can observe. This ancient light is known as the cosmic microwave background, or CMB, the afterglow of the Big Bang. It surrounds us on all sides, a faint whisper of heat in the microwave part of the spectrum that fills the sky day and night. Discovered in the 1960s as a uniform radio glow coming from every direction in space, the CMB is like a photograph of the infant universe, taken about 380,000 years after the Big Bang. At that epoch, the universe was an expanding fireball that had just cooled enough for electrons and protons to combine into neutral atoms. Before this recombination, matter and light were tightly coupled. The young universe was a brilliant opaque fog where photons bounced off free electrons constantly. Once neutral atoms formed, the fog cleared, space became transparent, and light was free to stream across the cosmos. That first light is what we now see as the CMB, cooled and stretched to microwave wavelengths after nearly 14 billion years of cosmic expansion. Today, it is extraordinarily cold and faint, just 2.7 degrees above absolute zero. But it is everywhere, an all-pervading memory of the universe's fiery beginning. For a long time, the CMB appeared almost completely uniform. No matter where you looked, it was essentially the same smooth temperature, a testament to the homogeneity of the early universe. But scientists believed there must be tiny irregularities, slight hot and cold spots, reflecting minuscule differences in density in those early times. After all, somehow those small density differences had to grow into galaxies and clusters later on. In 1992, a major breakthrough came when NASA's COBE, Cosmic Background Explorer, satellite finally detected the long-sought anisotropies, extremely subtle variations in the CMB's temperature across the sky. They were incredibly tiny differences, only about 1 part in 100,000, but they were real. To visualize it, imagine a flat, calm ocean with ripples just a few millimeters high. That's how smooth this radiation is. Yet those tiny ripples carry profound information. The lead scientist of the mission, George Smoot, famously said upon seeing the CMB map, "If you're religious, it's like looking at the face of God," reflecting the awe of revealing these primordial patterns. Those faint blotches and speckles on the COBE map were the imprint of density variations from the infant universe, the seeds from which all later cosmic structures grew. Subsequent missions, like NASA's WMAP, Wilkinson Microwave Anisotropy Probe, in the early 2000s, and the European Space Agency's Planck satellite in 2013, mapped the CMB in even greater detail and precision. These all-sky maps of the microwave background revealed a rich tapestry of slightly cooler and warmer spots, typically about a degree across on the sky. Cosmologists analysed the statistical patterns of these spots, essentially the texture of the early universe. What they found was a goldmine of information about the universe's composition. The sizes, and relative strengths of the ripples in the CMB act like a cosmic barcode, encoding values like the density of matter, the density of normal atoms, the expansion rate, and more. By fitting these patterns with theoretical models, scientists could deduce the recipe of the universe with unprecedented accuracy. And one of the clearest messages from the CMB was that dark matter is absolutely necessary to explain what we see. What does all this have to do with dark matter? The key is that those primordial ripples, essentially sound waves in the hot plasma of the early universe, were influenced by whatever components were present. Normal matter, the protons, neutrons, and electrons that make up atoms, interacts with light, so it felt the push and pull of radiation pressure in that primordial plasma. Dark matter, on the other hand, does not interact with light at all. It was free to start clumping under gravity, even while the photons kept normal matter from gathering. The presence of a substantial amount of dark matter changed the way those sound waves propagated. In the language of cosmologists, it altered the relative heights of the acoustic peaks in the CMB's power spectrum, a sort of musical frequency analysis of the pattern. In simpler terms, certain sizes of ripples in the CMB are a bit more pronounced, and others a bit muted, exactly in the way you'd expect if there was about 5 times more dark matter than ordinary matter in the universe. Without dark matter, the pattern of spots on the CMB would look markedly different. Because dark matter was present, gravity had extra pull in the early universe, which helped compress some of the ripples more strongly. When scientists include roughly 5 parts dark matter to 1 part normal matter in their models, the calculated patterns of CMB fluctuations line up beautifully with the observed ones. It was a striking confirmation that by 380,000 years after the Big Bang, and indeed well before that, dark matter was already out there, orchestrating the formation of structure. Moreover, the CMB data indicated that dark matter must have been cold, that is, made of particles moving much slower than the speed of light in the early universe. If the dark matter had been hot and fast-moving, for example composed of particles like energetic neutrinos, it would have smoothed out the smaller density fluctuations and prevented the tight clustering needed to form galaxies, as we observe. The fact that the cold dark matter model, with slow, heavy particles, matches both the CMB patterns and the later distribution of galaxies, is a strong validation of our cosmological theory. The CMB measurements not only confirmed the existence of dark matter, but they also nailed down its cosmic abundance. According to the best fits of those data, only about 15 to 20% of the matter in the universe is the normal matter that makes up stars, planets, and us. The rest, roughly 80 to 85% of all matter, is dark matter. Put another way, if you imagine all the matter in the universe as a pie, the slice made of atoms is just a small sliver compared to the vast portion made of dark matter. And that is just the matter content. The CMB data also revealed that an even larger component of the universe exists in the form of dark energy, about 68% of the universe's total energy content, a mysterious force driving the accelerated expansion of the universe. Dark energy is an enigma of its own, beyond the scope of our current journey, but its discovery underscores how much of the cosmos remains hidden or unexplained. As for dark matter, the CMB gave us extraordinary confidence that we know how much of it is out there, even if we still do not know what it is made of. Perhaps more importantly, the CMB gave insight into how dark matter helped shape the universe's grand structure. Those tiny density differences seen in the CMB were the starting points that would grow over time into galaxies and clusters. Dark matter's gravity was the engine of that growth. Because dark matter does not collide or interact with light, It began quietly collapsing into clumps and filaments early on, forming a sort of invisible scaffolding in the young universe. Once the universe cooled enough for normal matter to drop out of the radiation soup after the CMB was released, that normal matter could finally fall into the gravitational wells already seeded by dark matter. In this way, dark matter provided the framework on which ordinary matter could gather and form the first stars and galaxies. Without dark matter's head start, the cosmos would likely have taken much longer to develop the complex structures we see today. The CMB's message is that dark matter was essential from the very beginning. It helped the early universe transition from an almost featureless hot soup into a lumpy mix of matter that would eventually become the cosmic web of galaxies. To put it another way, when we gaze at the all-sky map of the CMB with its tiny freckles of temperature variations, we are looking at a blueprint of cosmic structure in its infancy. Dark matter's effect is etched into that blueprint. The fact that our observations match a universe with dark matter, and would make little sense otherwise, gives astronomers great confidence that we are on the right track in understanding the cosmos. The CMB is sometimes called the baby picture of the universe. And in that baby picture, dark matter's influence is already present, quietly guiding the development of everything that comes after. Armed with this knowledge from the CMB, astronomers have been able to create simulations and models that take those primordial conditions and evolve them forward over billions of years. What emerges from those simulations is a universe that develops a vast cosmic web of structure, much like the one we observe. And indeed, when we survey the real universe on large scales, we find that galaxies are arranged in just the patterns that these dark, matter-driven simulations predict. We turn now to that grand cosmic web, the immense network of galaxies and voids, to see how the invisible skeleton provided by dark matter has shaped the visible universe over time. Across hundreds of millions of light years, on the grandest scales we can imagine, matter in the universe is not scattered evenly. Galaxies gather in groups and clusters, and those clusters connect across space in tenuous chains, forming immense filaments. Between these filaments lie enormous voids, vast regions of space nearly empty of galaxies. This arrangement, a spongy, web-like pattern, is what we call the cosmic web. It is the largest scale structure we know, a kind of cosmic architecture that only becomes apparent when we survey the universe at immense scales. And it is yet another realm where the influence of dark matter makes itself known in a profound way. It wasn't until the late 20th century that astronomers really began to map the universe on such large scales. In the 1980s, pioneering redshift surveys, which measured the distances of galaxies, started to reveal an unexpected tapestry in the distribution of galaxies. Two astronomers, Margaret Geller and John Huchra, published one of the first slice maps of the universe, and in it they discovered a landmark feature, a colossal wall of galaxies stretching across at least 500 million light-years. They named it the Great Wall. This was a shock. No one had anticipated a structure of that size. Around the same time, astronomers also identified gigantic voids, such as the Boötes void, an almost spherical region tens of millions of light-years across, with hardly any galaxies in it. These discoveries were the first clear glimpse of the cosmic web. The universe looked almost like a vast foam, where galaxies inhabited the surfaces of bubbles and the interiors of the bubbles were nearly empty. As galaxy surveys became even more ambitious, mapping millions of galaxies, for example, the Sloan Digital Sky Survey in the 2000s, the pattern became unmistakable. On the largest scales, the distribution of galaxies resembled a network of filaments and nodes. Dense clusters of galaxies sit at the intersections of filaments, the nodes of the web, and between these nodes, the filaments span across huge distances. The image is evocative. Some liken it to a spider's web glittering with dew, where the dewdrops are galaxies tracing out the strands of dark matter. Others compare it to the neurons of a giant cosmic brain, or to the structure of sponge-like foam. In all comparisons, the idea is clear. There is a hidden order and connectedness in the arrangement of galaxies, an order dictated by gravity, following the blueprint laid out by dark matter. This grand pattern was not a complete surprise to theorists, because computer simulations of cosmic evolution had predicted something similar decades before, when cosmologists include dark matter in their models of the universe's formation. They start with the tiny density fluctuations indicated by the CMB and let gravity amplify them over billions of years. In these simulations, dark matter, making up the bulk of matter, pulls everything together, forming filamentary structures and dense knots. Ordinary matter, influenced by dark matter's gravity, falls into the same structures and eventually lights them up with stars. The end result of such a simulation is a wispy network very much like the observed cosmic web. Filaments of dark matter form first, and galaxies and clusters emerge along these filaments where enough ordinary matter accumulates to ignite star formation. The vast voids naturally arise in between, as regions that started off slightly less dense end up evacuating matter towards the growing filaments and clusters. The fact that our surveys of galaxies match the cosmic web patterns from simulations is a triumph for the dark matter theory. Without dark matter, we cannot easily explain the existence of such huge, coherent structures. If we tried to simulate the universe with only normal matter, the formation of galaxies and clusters would be drastically slower and less organized, because ordinary matter was held back by radiation in the early universe. The observed universe, rich in structure, simply would not have had enough time to develop its walls, filaments, and voids to the extent we see today. With dark matter in the picture, however, the web assembles efficiently. Gravity had a head start thanks to dark matter's early clumping, and that set the stage for everything else. Thus, the cosmic web is essentially a visual, statistical confirmation of dark matter's role in cosmic history. We see in the real universe exactly what we'd expect to see if dark matter wove the scaffolding from the beginning. Let's pause to consider the scale and beauty of this structure. Imagine a volume of space 1 billion light-years across. Within it, countless galaxies are strung along invisible tethers of gravity, congregating in clusters at the junctions. Those clusters, like the Coma cluster we met earlier, or the Virgo cluster closer to home, are the heavy nodes where many filaments converge. Each filament itself might span hundreds of millions of light-years, containing galaxies strung like pearls on a cosmic necklace, held together by long chains of dark matter. And then there are the voids, yawning expanses in between where galaxies are scarce. Standing at one edge of a void and looking toward the other side, a metaphorical thought experiment, since we cannot actually stand outside the universe, you would see galaxies delineating a distant wall, but very little in between. It is awe-inspiring to realize that this vast design, this web, with its intricate weave of matter and emptiness, was all seeded by tiny primordial fluctuations and shaped by dark matter's relentless pull. We often call dark matter the hidden scaffold, or the skeleton of the cosmos. And here, in the cosmic web, that analogy comes to life. The dark matter is like the invisible bone structure on which the visible universe is built. The bright galaxies and glowing gas trace out that structure, much as flesh might trace the shape of bones. In the densest clumps of the web, the clusters, both dark and normal matter pile up tremendously, anchoring the whole network. In the sparsest voids, even dark matter is relatively depleted, providing little gravitational pull to draw matter in. This cosmic network is a picture of balance, gravity and expansion, dark matter and ordinary matter, all interacting to create a universe that has both grand order and vast emptiness. Mapping the cosmic web continues to be a major enterprise in astronomy. With each new survey, we push further, seeing more of the universe's large-scale design. We also peer back in time. Light from distant galaxies shows us the universe when it was younger. Observations of faraway quasars and galaxies, billions of light-years distant, suggest that in those earlier eras, the cosmic web was indeed less developed. The filaments were thinner, the clusters smaller. Over billions of years, under the guiding influence of dark matter, the web became more pronounced, much like a developing organism growing into maturity. This temporal aspect gives us yet another confirmation. We can witness the cosmic web evolving in the way our dark matter models predict, growing from a more uniform state to the complex tapestry we see around us today. Looking at the cosmic web, we are gazing at dark matter's handiwork on the grandest canvas. Every galaxy, every cluster, positioned just so, following the contours of an unseen gravitational landscape. The agreement between what we observe and what our dark matter-driven theories predict is remarkable. It tells us that, despite not seeing dark matter directly, we have been able to map its effects with great success. The cosmic web stands as a majestic verification that we live in a universe where most of the matter is invisible, yet its presence is revealed in the very structure and distribution of all the galaxies. Each piece of evidence we've explored, the rotation of galaxies, the motions of clusters, the bending of light, the primordial whisper of the CMB, and the large-scale cosmic web, reinforces the others. Together, they paint a consistent picture of a universe structured by an unseen majority. Dark matter is the silent architect of this vast cosmic order. It allowed galaxies to form. It gives galaxy clusters their immense binding mass, and it connects everything in a grand design. The luminous universe we see is like the tip of a deep iceberg, with dark matter forming the massive, hidden body beneath the surface, guiding the visible into its beautiful array. Throughout our journey so far, a theme has emerged: the balance that dark matter brings to the cosmos. In a very real sense, dark matter is a cosmic foundation, providing the gravitational scaffolding for all the large-scale structures we see. It is the silent partner to the visible universe, working behind the scenes to allow galaxies and clusters to form and persist. This partnership between the unseen and the seen creates a kind of harmony in the cosmos. Think of a galaxy as a grand, spinning dance of stars. The luminous stars and glowing gas swirl in elegant patterns, forming spiral arms and bright cores, while an invisible halo of dark matter surrounds them, keeping the entire galactic dance in tune through its gravity. Without the dark matter's massive, stabilizing presence, the centrifugal force of those rotating stars would fling them outward, and the graceful whirl of the galaxy could not hold together. Conversely, without the ordinary matter, the dark matter halo would be a sterile framework. Massive, yes, but without the spark of starlight, without planets, without life as we know it. Together, visible and dark matter create a balanced whole. Dark matter provides the structure and gravity. Ordinary matter provides the radiance and the rich complexity that arises within that structure. This balance is evident not only within individual galaxies, but across the vast expanse of the cosmic web. In that web, dark matter outlines the grand design, and ordinary matter traces that design, lighting it up just enough for us to perceive. There is a dynamic equilibrium at play. Gravity, largely contributed by dark matter, pulls matter inward, drawing structures together, while the expansion of the universe, aided in recent epochs by dark energy, pulls outward. For billions of years, dark matter's gravity was the dominant influence on local scales, slowing the expansion in regions of higher density and enabling the growth of galaxies and clusters. In more recent cosmic times, dark energy has begun to dominate the expansion of space, pushing galaxies apart on the largest scales. Yet, the structures that dark matter helped form remain bound in their own regions, creating a cosmic landscape of clustered realms separated by growing voids. The amount of dark matter, relative to everything else, was just what was needed to foster the universe we see. It's as if the cosmos was tuned to a near-perfect recipe. Had there been significantly less dark matter, the early density fluctuations might not have grown enough to form galaxies by now, leaving a sparse, almost empty universe with few stars. Had there been significantly more dark matter, its overwhelming gravity might have led to galaxies forming too early and too dense, or even collapsed the universe back on itself before it had time to age gracefully. In our universe, the proportions have allowed for a remarkable outcome: a vast cosmic ecosystem where galaxies can grow and survive for billions of years, stars can live out their lives, and on at least one tiny planet, creatures can emerge to contemplate it all. From this perspective, dark matter is not just an astrophysical oddity. It is a central player in the story of why our cosmos is so structured and hospitable to complexity. It has choreographed the dance of galaxies and underpinned the formation of everything from the first stars to the gigantic clusters we observe today. Every glittering galaxy in the night sky owes its existence, in part, to the gravitational scaffolding of dark matter that gathered the material to form it. Even our own Milky Way, with its sweeping spiral arms and multitude of suns, sits within an enormous dark matter halo that provided the gravitational well to collect gas and dust and birth our stellar neighborhood. In a poetic sense, we owe our existence to this dark, invisible substance. Without it, our galaxy might never have come together in a way that allowed the sun and earth to form. It's humbling to realize that something we cannot even see has played such an indispensable role in creating the conditions for life. This realization also reminds us how special the familiar matter around us actually is. We humans, and everything we directly interact with, are made of ordinary atoms, the rare stuff of the cosmos. We live our entire lives immersed in what amounts to the cosmic minority, blissfully unaware through most of history that the dominant form of matter is something utterly different and invisible. Only in the last few decades have we recognized that most of the matter in the universe is of a type we have yet to identify. It's a striking lesson in modesty. We are built from the exception, ordinary matter, while the rule, dark matter, floats unseen in the vastness around us. For thousands of years, we gazed at the heavens, believing that the universe we saw was all there is. The revelation that an invisible framework underlies the cosmic order is both humbling and exhilarating. A reminder that even now, profound mysteries await discovery in the space between the stars. The journey to uncover dark matter's secrets is one of the great scientific adventures of our time. We have amassed overwhelming evidence that dark matter exists and understand how it behaves on large scales, gravitationally sculpting the cosmos. Yet we still yearn to know, what exactly is it? Is it a new kind of elementary particle left over from the Big Bang, drifting through us as a wispy sea of undetected mass? Could it be a whole family of different particles? Or something even more exotic, like multitudinous tiny black holes, or a property of gravity we haven't fathomed? So far, dark matter has eluded all attempts at a direct detection. Around the world, scientists are devising ingenious experiments to find it. Deep underground laboratories house enormous detectors chilled and shielded from interference, waiting for the faintest bump of a dark matter particle colliding with normal matter. High up on mountains and in space, telescopes scan for high-energy signals or subtle effects that could betray dark matter particles, annihilating each other in distant galaxy halos. At particle accelerators like CERN's Large Hadron Collider, physicists hope to perhaps create dark matter in high-energy collisions, watching for an imbalance in momentum as possible invisible particles fly off. Each of these efforts is essentially shining a flashlight into the darkness, hoping to catch a glimpse of the shadowy substance that pervades our universe. So far, dark matter remains elusive in these direct searches, heightening the mystery. We have inferred its presence confidently through astronomy, yet in the laboratory it hides silently. This has led some to speculate about alternatives. Could it be that our theory of gravity needs revision rather than invoking unseen mass? A few theories, like MOND, modified Newtonian dynamics, try to explain galaxy rotation without dark matter, but such ideas struggle to account for the full range of evidence, especially objects like the bullet cluster, where gravity's effects clearly separated from ordinary matter. At this point, the vast majority of scientists are convinced that dark matter is real and is likely some form of particle or substance we simply haven't identified yet. Thus, the quest continues. Dark matter stands as one of the most profound, outstanding questions in science. Its solution could revolutionize physics, opening up a new understanding of the components of the universe. It's a quest that requires us to blend cosmic observation with cutting-edge particle physics, to look both outward and inward. On the cosmic scale, we map its influence across space and time. On the microscopic scale, we hunt for its essence in detectors and theories. As we reach the end of this chapter of our exploration, one thing is clear. The story of dark matter is far from over. In fact, in many ways, it has only just begun. We have identified the fingerprints of this invisible presence and traced its role in shaping the cosmos. But the true identity of the dark remains in the shadows. The next steps in this grand investigation will delve into that mystery, trying to bring the dark matter to light, literally and figuratively. The wonder of it all is that the universe, in revealing this deep secret, has invited us to keep asking questions, to continue the journey. For now, let the sense of awe and curiosity linger. The darkness that fills so much of the cosmos is not empty. It is full of unseen mass and potential revelations. The night sky, with all its stars and galaxies, owes much of its existence to this dark symphony playing out beyond our sight. As we prepare to venture further into understanding this cosmic mystery, we carry with us the knowledge gained so far and the excitement of what lies ahead. The hidden skeleton of the universe has been unveiled, but the nature of its bones remains unknown. It is a mystery that calls to us, inviting us onward into the depths of space and the frontiers of physics in search of the answers that will illuminate the darkness. The cosmos stretches out in silent darkness, yet all around us lies an unseen presence. We have traced the evidence of this invisible mass, the mysterious dark matter that holds galaxies together and shapes the cosmic web. It comprises about 85% of all the matter in the cosmos, far more than the ordinary atoms we see. Without this hidden mass, galaxies would fly apart, and the universe would look vastly different. Now our journey leads us into one of the most compelling paths scientists have explored, the idea that dark matter might be made of undiscovered particles. It's a quest to find the universe's missing building blocks, elusive particles that fill the halos of galaxies like a hidden sea, silently guiding the formation of structures in space. For decades, physicists have imagined that dark matter could be composed of tiny, invisible particles drifting all around us. Among these, one idea took center stage early on: the notion of weakly interacting massive particles, or WIMPs. In spirit, scientists envisioned WIMPs as akin to neutrinos, those ghost-like particles we already know that pour out of the sun, but far heavier and thus capable of shaping cosmic structure. Trillions of neutrinos stream through your body each second without leaving a hint. But neutrinos have almost no mass and zip around at nearly light speed, so they cannot hold galaxies together. Neutrinos, for all their abundance, simply flit through the cosmos without ever gathering into the massive halos that dark matter requires. WIMPs, by contrast, would move slowly and carry heft, behaving like neutrinos' weighty, sluggish cousins. They would slip through the spaces between atoms just as easily, remaining invisible and undetected, yet their collective gravity could sculpt galaxies and clusters. It was a simple yet profound proposition. If dark matter were made of such heavy, elusive particles, it would form an unseen scaffolding for the cosmos, massy enough to tug on stars and galaxies, yet so intangible that it never blazes or glows. WIMPs captured the imagination because they fit hand in glove with our understanding of the early universe. In the hot aftermath of the Big Bang, countless particles were born, collided, and transformed. Most of those either decayed away or coalesced into the atoms and light we know. But if WIMPs existed, they would have been produced in abundance in those first fiery moments. Then, as the universe expanded and cooled, many would have survived, moving too sluggishly to annihilate each other entirely. By an intriguing coincidence often called the WIMP miracle, a particle interacting via the weak nuclear force and weighing roughly tens or hundreds of times the mass of a proton would naturally be left over in about the right amount to explain today's dark matter density. It was as if the universe itself were hinting at WIMPs through a cosmic balancing act. The WIMP hypothesis became something of a guiding star for dark matter research. Throughout the 1990s and early 2000s, it dominated scientific discussions on the topic. Researchers calculated how WIMPs would freeze out in the early universe, how they would clump into halos, and what signals they might produce for our instruments. Many were convinced that discovering WIMPs was only a matter of time and incremental improvement in our experiments. The appeal of the idea was not just cosmological bookkeeping. It also found a ready home in theoretical physics. For years, physicists had been extending the known laws of nature and wondering if every particle we know might have an unseen partner, a heavier sibling lurking just out of reach. This line of thought led to the concept of supersymmetry, a proposed symmetry of nature that doubles the particle roster. In supersymmetry, electrons, quarks, and all familiar particles would each have a partner particle. Crucially, the lightest of these new superpartners could be stable, electrically neutral, and interact only weakly. This hypothetical particle, often a mixture of supersymmetric siblings of the photon and Higgs boson, was nicknamed the neutralino, and it rose as a prime dark matter candidate. A neutralino would be a WIMP by nature, heavy, slow-moving, and exceedingly shy in how it interacts. It wouldn't emit light, it would feel gravity, and it would rarely, if ever, bump into normal matter. On paper, it was an excellent match for the dark matter we needed. Picture these WIMPs and neutralinos as cosmic drifters. Trillions might be streaming through your living room right now, like a gentle, invisible wind. You don't feel them at all, because they slip effortlessly through the spaces between atoms. Only on the rarest occasions would one ever collide with a piece of ordinary matter. This ghostly behavior is exactly what dark matter demands. Something massive enough to tug on stars and galaxies, yet so intangible that it never shines or interacts strongly. Through the late 20th century and into the 21st, WIMPs led the pack in the race to explain dark matter. They offered a beautiful solution on paper, and early computer simulations of cosmic structure formation backed them up. When scientists put WIMPs into their models as the dark ingredient, galaxies and clusters emerged in those simulations, much like the ones we observe in reality. The idea of cold dark matter, heavy, slow particles, produced a universe with galaxies of the right sizes and distributions. By contrast, if one tried hot dark matter made of fast, light particles, like neutrinos, the small-scale structures, dwarf galaxies and details of galactic cores, would blur out and fail to form properly. The success of the cold dark matter model, with WIMPs as its archetype, made it seem as if the puzzle pieces were finally falling into place. Yet, no matter how elegant a hypothesis, it must face the test of reality. And so began an intense worldwide effort to actually find these elusive WIMP particles. If they truly permeate our galaxy, scientists reasoned, perhaps we can catch one in the act of interacting. The idea of a direct encounter with dark matter fired imaginations. Plans were drawn to build super-sensitive detectors deep underground, hoping to hear the faintest tap of a WIMP hitting an atomic nucleus. At the same time, others prepared to use powerful particle accelerators to create WIMPs in high-energy collisions. For a while, optimism ran high. By the early 2000s, experimental techniques had advanced rapidly, and it felt like a discovery could be just around the corner. However, as the years passed, WIMPs remained true to their ghostly nature. No unmistakable sign of them materialized. One by one, experiments reported only silence, where a WIMP's whisper might have been expected. The once simple picture grew increasingly complex. Perhaps the WIMPs were lighter or heavier than originally thought, or perhaps they interacted even more weakly than we'd hoped. Bit by bit, the range of possible hiding spots, in terms of particle mass and interaction strength, was narrowed. The WIMP miracle that had seemed so tantalizing began to feel more like a mirage, a guiding vision that led us onward, but always evaporated at the horizon. By the mid-2020s, many physicists found themselves reflecting on the long chase for WIMPs. Decades of searching had dramatically improved our experimental sensitivity. Detectors had become so refined that they were starting to pick up signals from particles we do know. For instance, faint interactions from neutrinos produced in the Sun and other cosmic sources were finally being detected. On the one hand, this was a triumph. It meant our instruments had reached the incredible precision needed to sense the ghosts of the known particle world. On the other hand, it was a frustration. Those very neutrinos act like an unremovable fog, obscuring potential WIMP signals. This neutrino background in our detectors creates a noise that can easily masquerade as the very thing we seek. In effect, experiments have grown so sensitive that they are bumping up against what's called the neutrino floor, a natural limit where neutrino interactions become a dominant source of events. It's a milestone. We've become sensitive enough to detect the cosmic neutrino background in these dark matter instruments, a remarkable achievement. But it also means the easy progress is ending. To push further, future experiments might need to find clever ways to tell a neutrino from a dark matter particle, perhaps by sensing the direction of each recoil, since neutrinos mostly come from the sun's direction. Innovative ideas are being proposed to break through this potential ceiling and keep the hunt alive beyond this foggy barrier. Still, even as they confront these challenges, researchers haven't given up on WIMPs entirely. The absence of evidence is not evidence of absence, as the saying goes. WIMPs have not been seen so far, but they have also not been conclusively ruled out. Some niches of parameter space remain in the shadows of our data, corners of possibility where WIMPs could still lurk unseen. New experiments on the horizon might yet catch a glimpse of a heavy, slow-moving dark particle. And theoretical physics has a way of reinventing itself. Even if the classic WIMP of early theories stays elusive, variants of the idea continue to emerge. Perhaps dark matter isn't a neutralino, but a similar entity born of a different theory, or maybe WIMPs interact in ways we hadn't imagined, hiding their effects more cleverly. In the grand game of cosmic hide-and-seek, WIMPs had long led our expectations and spurred tremendous advances in technology and understanding. But as time went on with no capture, the scientific community began to open its mind to other possibilities. While many researchers were chasing WIMPs, another set of ideas fluttered at the fringes of mainstream physics. Ideas that were lighter, even more elusive, and in some cases downright strange. If the heavyweight WIMPs refused to show themselves, could dark matter instead be something at the opposite end of the spectrum? Enter the world of ultralight particles and exotic phenomena. Enter the axions and their kin, the other shadows that might populate the dark side of the universe. Among these exotic possibilities, axions stood out as particularly intriguing. Axions were first proposed not to solve the dark matter mystery, but to fix a subtle issue in the theory of quarks and gluons, the particles that make up atomic nuclei. In the 1970s, to explain why certain symmetries in nature appeared unbroken against expectation, physicists conjured up a new particle, an ethereal, nearly massless particle that would gently balance the equations. This particle was named the axion, a whimsical nod to a popular laundry detergent, because it would clean up the theoretical problem. For a long time, axions were a mere theoretical footnote, interesting in concept, but with no evidence of being real. Then came the realization. If axions exist, they could have been produced in enormous numbers during the early universe. And though each axion would be incredibly light, far lighter than even a single electron, their sheer abundance could mean that collectively they weigh as much as all the dark matter needed. In other words, axions could form a vast, invisible field permeating space, contributing mass and gravity without emitting any light. Imagining axion dark matter pushes us into a very ghostly realm. Unlike WIMPs, which are chunky and particle-like, think of them as tiny billiard balls drifting through space, axions would be almost wave-like in behavior due to their tiny mass. Instead of clumping into small particles, axions would form a smooth, oscillating field that stretches across entire galaxies. The dark matter, made of axions, would be more like a subtle, pervasive mist, or a field of gentle vibrations, rather than a gas of discrete particles. It's an exotic concept, a substance that is both particle and wave, spread throughout space, whispering gravity into the fabric of the cosmos, without ever pinging our detectors directly. Scientists who grew curious about axions devised clever ways to search for them. But how do you catch something that barely interacts at all? Axions, if real, would interact even more weakly than WIMPs. They don't even feel the weak nuclear force. Thankfully, there is one narrow window to exploit. Axions might slowly and occasionally turn into photons, particles of light, in the presence of a strong magnetic field. It's as though an axion passing through a magnetic field could, in a moment of reveal, convert into a particle of light. Based on this idea, experiments were built that are part radio receiver, part magnet, and part quantum amplifier. In a quiet laboratory space, scientists set up large, powerful superconducting magnets surrounding hollow metal cavities, essentially tunable microwave resonators. Instruments like the Axion Dark Matter experiment, ADMX, and similar haloscope experiments are listening for a very specific and faint tone. The signal of axions transforming into microwave frequency photons inside the cavity. The magnet acts like a catalyst, coaxing any passing axion to reveal itself, and the cavity is tuned like an ear, straining to hear a particular pitch amid the silence. In practice, the axion hunt is slow and methodical. Researchers gradually adjust the cavity's tuning, sweeping through one tiny frequency band at a time, as if turning a radio dial through static in hope of a faint note. Each frequency must be listened to for long enough to catch a potential whisper, often days or weeks, before moving to the next. Scanning a wide range can take years, and so far every channel has come up silent. Yet with ever more sensitive equipment, the search continues, ears open for that elusive cosmic note that would announce the presence of axions. As of the mid-2020s, no definitive axion signal has been caught, but the search is intensifying. Axions remain compelling because they solve two puzzles at once. They tidy up a nuance in particle physics, and they could naturally be the dark matter. Unlike WIMPs, which were invented solely to explain dark matter and have no other role in our theories, axions had an independent reason to exist, to resolve that quark theory issue, and dark matter was a second brilliant opportunity for them to shine, figuratively speaking. This dual motivation keeps axions high on the list of dark matter contenders, especially as traditional WIMPs stay elusive. Beyond axions, the family of potential dark matter particles includes many other shadows, strange and inventive possibilities dreamt up by theorists. Some scientists consider the notion of dark photons, particles like photons, the carriers of light, but belonging to a hidden force that only dark matter feels. If dark matter has its own secret forces and interactions, a whole dark sector, it might mean there is an entire hidden realm of particles, a mirror world that interacts with our familiar world only through gravity or the tiniest of portals. In that picture, dark matter might not be just one particle, but a collection of particles with their own dark interactions, forming possibly dark atoms or dark radiation, an entire shadow ecosystem that coexists with our universe unseen. Another candidate that has emerged over time is the idea of a sterile neutrino. We already know of three types of neutrinos: electron neutrinos, muon neutrinos, and tau neutrinos. Ghostly, nearly massless particles that stream out of the sun and other reactions, rarely interacting with matter. A sterile neutrino would be a fourth kind, even more aloof. It wouldn't participate in the usual weak nuclear interactions that regular neutrinos do. It would only reveal itself via gravity, and a tiny bit through mixing with the regular neutrinos. If a sterile neutrino has a mass, perhaps a few thousand times heavier than a regular neutrino, still much lighter than a typical WIMP, it could be a viable dark matter candidate. Such a particle would be classified as warm dark matter, not zipping around as fast as a neutrino, hot dark matter, but not as stationary as a heavy WIMP, cold dark matter. A warm dark matter particle like a sterile neutrino would move a bit faster and could smooth out some small-scale structures in the universe. This idea is intriguing because it might help with certain cosmic puzzles. For instance, it could reduce the number of tiny satellite galaxies and make galaxy cores less dense, addressing some discrepancies between observations and cold dark matter simulations. Experiments and observations have tried to find hints of sterile neutrinos. One possible sign could be a faint X-ray glow in space produced when a sterile neutrino decays. In fact, some scientists have reported a curious X-ray emission line at around 3.5 keV coming from galaxy clusters, which doesn't match any known atomic line. One hypothesis is that it could be caused by the decay of a sterile neutrino dark matter particle. However, this too remains controversial and unconfirmed, with many experts arguing it could have an astrophysical origin. Like other exotic possibilities, sterile neutrinos remain a tantalizing idea awaiting clearer evidence. All these exotic possibilities, axions, dark photons, sterile neutrinos, and more, illustrate a humbling point. Dark matter could be a whole menagerie of the unexpected. When scientists list out candidates, it sometimes reads like a catalogue of science fiction concepts given serious consideration. From ultralight fuzzy dark matter, particles so extremely light that their quantum wave might stretch across a galaxy, gently smoothing out small-scale structures, to super-heavy wimpzilla particles left over from the Big Bang, to hidden dimensions or tiny black holes. We truly don't know what form the answer will take. Each candidate arises from a different corner of theory, and each demands a different method of search. Yet even as dark matter theory thrives on big scales, there are subtle cosmic conundrums on smaller scales that attract attention. For example, computer simulations using cold, collisionless dark matter tend to predict more tiny satellite galaxies around large galaxies than we actually observe, and they often produce very dense cusp distributions of dark matter in galactic centers. Real galaxies, especially small dwarf galaxies, appear to have fewer satellites and more diffuse, chord central profiles. These discrepancies, known as the missing satellites problem and the cusp core problem, have led some to wonder if our dark matter particles have additional properties that we haven't accounted for. Perhaps dark matter particles can bounce off each other a little, spreading out the density in galaxy centers. This is the idea of self-interacting dark matter. Or maybe the particles aren't entirely cold, but somewhat warm, moving fast enough to erase the smallest clumps, as would be the case for a particle like a sterile neutrino. A warm dark matter particle would inhibit the formation of very small galaxies, which could align better with observations. At this point, these ideas remain speculative, but they show that even once we identify what dark matter is, we will need to understand its behavior in rich detail. The microphysical properties of dark matter. Does it collide with itself? Is it exactly cold or a bit warm? Could have noticeable effects on the arrangement of galaxies and stars. Uncovering dark matter isn't just about naming the particle, it's about understanding how it shaped the universe, from the largest scales down to individual stellar systems. While the idea of new particles dominates the dark matter discussion, it's not the only path that was explored. In fact, before exotic new particles and WIMPs took over the spotlight, some researchers asked a more down-to-earth question. What if dark matter isn't exotic at all? Could it be made of ordinary matter in extraordinary places? This line of thinking led to one of the earliest alternative dark matter hypotheses. Perhaps the universe is filled with massive compact halo objects, endearingly termed MACHOS. The macho idea proposed that the halo of our galaxy, the vast spherical cloud of unseen mass enveloping the Milky Way, might be composed not of new particles, but of a multitude of faint, non-luminous objects. These could be things like brown dwarfs, failed stars that never ignited into shining starlight, rogue planets drifting in interstellar space, old white dwarf stars that have cooled to the point of invisibility, or even black holes, either the remnants of dead stars or primordial black holes born in the early universe. None of these objects emit significant light on their own, so they would effectively be invisible against the darkness of space. The question was, could all these unilluminated objects collectively account for the gravitational heft we attribute to dark matter? It was a compelling notion in the 1980s and early 1990s, especially because it didn't require conjuring new physics. It just required a lot of normal stuff hidden in hard-to-see forms. To test it, astronomers needed a method to detect dark objects that emit little or no light. Fortunately, Einstein's theory of gravity offers just the method: gravitational lensing. If a compact, massive object passes in front of a distant star from our point of view, the object's gravity will act like a lens, bending and focusing the star's light. The star would momentarily appear brighter, since its light is being concentrated toward Earth. This effect is called microlensing. Micro, because the lensing is too small to produce multiple separate images of the star. Instead, we see a single star whose brightness changes over time in a characteristic way. In the 1990s, teams of astronomers undertook ambitious observing campaigns to catch these rare microlensing events. Projects like MACHO, which lent its name to the objects, EROS, and OGLE turned their telescopes toward dense fields of stars in our galaxy and in the neighboring Magellanic Clouds, monitoring millions of stars night after night. They were looking for the telltale sign, a star that unexpectedly grows brighter over days or weeks, and then dims back to its usual intensity. A transient, symmetric brightening that can't be explained by the star's intrinsic behavior. If observed, such an event would signal that an unseen mass drifted through our line of sight, magnifying the star's light for a time. The night skies did yield some results. A number of microlensing events were indeed observed. For example, one of the early microlensing detections involved a star in the large Magellanic Cloud, gradually brightening over about 40 days, then fading back to normal. Such a smooth, symmetric increase and decrease in light was exactly the expected signature of an invisible lens passing by. It was breathtaking for the astronomers to realize that they had witnessed the gravitational footprint of an unseen object, potentially a dim star or a black hole, revealing itself only by warping the light of a background star. Each such event, when spotted, was a triumph. It meant a dark object out there, maybe a faint star, a drifting planet, or a massive remnant, had made itself known purely through gravity's subtle lensing effect. The early results showed more microlensing events than one would expect from just the known stellar population, hinting that indeed there were unseen masses in the halo. However, as more years of data were collected, a clearer picture emerged. The surveys found that these microlensing events, while definitely occurring, were not common enough to account for all of the dark matter. The number of events observed was too low. If the Milky Way's halo were full of faint stars or black holes making up all the dark matter, the experiments should have seen hundreds of events. Instead, they saw only a few dozen. The conclusion was that MACHOs could contribute at best a small fraction of the dark matter, certainly not the lion's share needed to explain the missing mass. One particular variant of the MACHO idea received renewed attention in recent years: primordial black holes. Unlike black holes that form from collapsing stars, primordial black holes would have formed in the ultra-dense environment of the early universe, perhaps from extreme fluctuations in the moments after the Big Bang. These black holes could, in theory, have any mass, from tiny asteroid mass ones to giants thousands of times heavier than the Sun. If a multitude of them formed, could they be the dark matter? For a time, primordial black holes seemed like an intriguing loophole. The microlensing surveys were most sensitive to objects around the mass of the Sun, so they might have missed very small black holes or very large ones. When the LIGO experiment began detecting mergers of unexpectedly heavy black holes, around 30 times the Sun's mass, in 2015, some speculated, could those be primordial black holes comprising some of the dark matter, bumping into each other occasionally? However, the window for primordial black holes being the entirety of dark matter has been steadily closing as well. New gravitational lensing searches, cosmic microwave background analyses, and gravitational wave observations have set traps for black holes across a wide range of masses, and most of those traps have caught nothing. If too many black holes of a given size existed, we would see their effects. And we largely don't. By current understandings, primordial black holes could make up only a modest fraction of the dark matter, unless they lie in a very specific, hard-to-test mass range. The cosmos, it appears, doesn't have enough MACHOS to do the job. Thus, the Macho hypothesis, once an appealing no new particles needed solution, largely faded from favour. The results pointed back to something more exotic. Dark matter likely isn't made of normal atoms or compact objects at all, but of something fundamentally different. In a way, the Macho searches forced us to admit that the darkness was deeper than just faint stars. It was something new. With dim stars and massive remnants mostly ruled out, the hunt pivoted fully back to the particle frontier. If dark matter is indeed something invisible and fundamentally new, how can we detect it? Scientists have pursued two complementary strategies. One approach is to listen for dark matter here on Earth, to wait for it to interact in a quiet, sensitive detector. This is known as direct detection. The other approach is to create dark matter in a controlled setting, to make it by colliding known particles at high energies and looking for traces of the dark ones. This is the collider search. In between, there's also a third approach, to look out into space for the products of dark matter interactions, essentially to see if dark matter particles break themselves by annihilating or decaying and leaving an observable mess. These are indirect searches. Scientists often sum up these strategies as shake it, make it, or break it. The shake it corresponds to direct detection, hoping a dark matter particle will shake a detector's target. Make it refers to producing dark matter in particle accelerators, and break it refers to catching signals from dark matter destroying itself in space. Deep underground, in laboratories nestled beneath mountains, or in old mine shafts, the stage was set for perhaps the most delicate game of hide-and-seek in scientific history. To reach one of these rarefied labs, you might descend in an industrial elevator for many minutes, plunging deep beneath the Earth's surface. At the end of the ride, a tunnel opens into a cavern carved out of ancient rock, and the atmosphere becomes cool, still, and hushed. Walls of concrete, steel, and water surround the central experiment to absorb stray radiation. Technicians and scientists tread carefully here, mindful of the extraordinary sensitivity of their apparatus. In this sanctuary of silence, even the faint tick of a Geiger counter would be too loud. Every component of the detector, from its sensors to its shielding, has been meticulously purified to eliminate natural radioactivity. It is a place designed to be as quiet as possible, so that if a dark matter particle finally knocks, we will be ready to hear it. That is why these experiments operate far from the bustle of the surface world, to escape the constant rain of cosmic rays and other background noise that could drown out a whisper of dark matter. Over a kilometre of solid rock or earth overhead serves as a natural shield, filtering out the charged particles that cascade through the atmosphere. In these subterranean sanctuaries, the detectors can listen more intently. They are built from ultra-pure materials to minimize any trace of radioactivity that could mimic a signal. The result is a kind of cathedral of silence, enormous vats of liquid kept in darkness, or crystals chilled to near absolute zero, all surrounded by layers of shielding and bathed in stillness. Here, scientists wait patiently in the dark, their instruments' ears perked, for the faintest ping that would betray a dark matter particle's presence. Different experiments use different detection methods, but the principle is the same. One leading approach involves large tanks filled with liquefied noble gases like xenon or argon. If a passing dark matter particle strikes an atom of this heavy liquid, it can jostle the atom's nucleus and produce a tiny flash of light and a bit of electric charge. Photomultiplier tubes or silicon sensors lining the tank will catch any such flash and amplify it. Another approach uses solid-state detectors, ultra-pure crystals of germanium or silicon kept at cryogenic temperatures. If a dark particle hits an atom in the crystal, it makes the crystal lattice quiver ever so slightly, generating a minuscule heat or electrical pulse that sensitive electronics can detect. There are also bubble chambers, vessels of transparent liquid held right at the brink of boiling. In those, a particle interaction can trigger a single tiny bubble to form, like a silent pop recording the particle's passage. Each technique has its advantages, and together they cover different possible types of dark matter interactions and masses. As the quest grew, these experiments also grew larger and more refined. In the United States, a detector called LUX, and its successor, Lux Zeppelin, was set up deep in a South Dakota gold mine, its heart a tank of liquid xenon kept ultra-pure and still. Beneath a mountain in Italy, the XENON series of experiments likewise watches a pristine pool of liquid xenon for any tiny flash of a collision. China's Panda X experiment has joined the search, and laboratories in Canada and elsewhere in Europe have also built their own dark matter detectors. Despite being spread across the globe, these teams share a common purpose and a sense of camaraderie. If one lab ever hears that telltale whisper of dark matter, the others will quickly try to confirm it. A discovery of such magnitude must ring true in multiple places for scientists to believe it at last. Year after year, these experiments have pushed their sensitivity to new heights. In the early days, a detector might have only caught a WIMP if it collided once a day or more. Now, the latest generations could detect interactions as rare as 1 per many tons of material per year. It's as if our ears have grown incredibly keen, straining to discern a single pin drop in a vast arena. And yet, so far, the dark matter pin has not dropped, at least not in a way we can be sure of. There have been moments of excitement, occasional blips in the data that made scientists hold their breath. In Italy, the Dharma/Libra experiment, using special sodium iodide crystals, has for years claimed to observe a curious annual fluctuation in their event rate, a pattern that rises and falls with the seasons. Why would that be exciting? Because if the Earth is moving through a cloud of dark matter as it orbits the Sun, there should be a slight wind of dark matter particles that is stronger at one time of year, when Earth's motion aligns with the Sun's motion through the galaxy, and weaker 6 months later, on the opposite side of its orbit. Remarkably, Dharma's data does show an annual modulation that matches this expectation. It was one of the earliest and most persistent tantalizing hints that dark matter might have been sensed. However, the story is far from settled. Other experiments using the same material have not confirmed this modulation. To chase down this puzzle, other groups around the world have set up their own sodium iodide detectors. In Spain and in South Korea, long-running experiments have monitored for the same yearly ebb and flow of signals. So far, they have seen no such effect. This absence has only deepened the mystery. Perhaps something unique to the original Italian experiment, its location, its materials, or its analysis, is creating a spurious signal. Or conceivably, dark matter interactions might be more complex than we assumed, showing up under one set of conditions and not another. For now, the Dharma hint remains unconfirmed and controversial, a stubborn ghost in the data that keeps the field both intrigued and cautious. Other experiments, too, have seen puzzling events. Over the years, detectors like COGNT, CDMS, and CRESS-ST reported a handful of candidate signals, little sparks in the dark that looked like what a WIMP might do. Each time, there was a ripple of excitement. Could this be it? But with more data and cross-checks, those hints often faded. In some cases, an apparent signal was later traced to an unexpected background or an experimental quirk. In others, no other experiment observing the same energy range saw anything similar, casting doubt on the claim. This pattern has repeated itself. A promising blip or bump in the data drums up speculation, only to be explained away or not corroborated by further investigation. The path to discovery is rarely straight. It's full of false starts and tantalizing distractions. And then there is the cosmic backdrop we mentioned earlier. Neutrinos. Unwanted as they may be in this context, neutrinos are a real source of events in these detectors. They are not dark matter, they're far too light and fast to explain galaxies, but they behave similarly in our instruments. A neutrino can hit a nucleus and produce a tiny recoil, just as a dark matter particle would. As detectors become more sensitive and larger in scale, they inevitably start picking up neutrinos from natural sources, primarily the Sun, but also cosmic ray interactions in the atmosphere and even distant supernovae. Eventually, these neutrino interactions become frequent enough to act like a steady murmur in the data, a background one cannot easily distinguish from what a dark matter signal would look like. This limit is poetically known as the neutrino floor. It's not an absolute dead end, but it's a daunting barrier. If a dark matter particle's interaction rate is below that floor, then our detectors will see so many neutrino-caused events that picking out a dark matter event becomes extremely difficult, like trying to hear a whisper in a room full of whispering people. It's a triumph of technology that we have reached the brink of the neutrino floor. Our detectors have become sensitive enough to detect neutrinos, which was once considered nearly as hard as detecting dark matter itself. But it presents a serious challenge for the next steps. To push beyond this floor, scientists are brainstorming new strategies. One idea is to build detectors that can not only measure the energy of a recoil, but also its direction. If we could tell which way a particle came from when it hit an atom, we might separate solar neutrinos, which mostly come from the Sun's direction, from dark matter particles, which would come from the galaxy's halo, and thus create a sort of wind, mostly from one direction of the sky, perhaps roughly the direction of the constellation Cygnus, due to our motion through the galaxy. Another approach is to use different target materials and compare signals, or to go to even more remote locations, like deeper underground or into space, to reduce backgrounds. Innovative ideas like these are being proposed to ensure the hunt can continue even as we approach this fundamental limit. Meanwhile, as the underground detectors keep their vigil in silence, other scientists have turned their instruments to the heavens, searching for any subtle whispers of dark matter out in space. If dark matter particles can annihilate each other or decay, they might produce ordinary particles or radiation that we could potentially observe. For example, two dark matter particles might collide and convert their mass into a burst of high-energy light, gamma rays. So researchers have used space-based observatories and ground telescopes to look for unexplained glows or flashes of gamma rays in places where dark matter is thought to be abundant, such as the centers of galaxies or dwarf galaxies orbiting the Milky Way. Likewise, dark matter particles might occasionally decay or interact to produce charged particles. An excess of certain particles in the cosmic rays that constantly bombard Earth could be a clue that dark matter is breaking itself into familiar particles. To probe this possibility, detectors on high-altitude balloons and satellites sift through incoming cosmic rays, looking for any unusual spikes in particles like positrons, anti-electrons, or antiprotons that can't be readily explained by known sources. Over the years, a few curious signals have indeed turned up from these indirect searches. The Fermi Gamma Ray Space Telescope, for instance, detected a faint glow of gamma rays at the center of our galaxy that doesn't neatly match any known astrophysical emission. Some scientists have suggested this galactic center GeV excess, as it's called, could be the hallmark of dark matter particles annihilating each other in that dense region. Similarly, experiments like Pamela and the AMS-02 spectrometer on the International Space Station found more high-energy positrons in the cosmic rays than expected. Under ordinary circumstances, high-energy positrons are relatively rare, and their surplus made physicists raise their eyebrows. One possible source for extra positrons could be dark matter particles annihilating in the galaxy and producing electron-positron pairs. For a while, these findings generated a flurry of excitement that perhaps we were catching glimpses of dark matter's effects indirectly. But as with many aspects of dark matter, nature has proven tricky. The gamma-ray excess at the galactic center might also be explained by a multitude of undetected millisecond pulsars, rapidly spinning neutron stars congregated in that region, an entirely ordinary, if unexpected, source of gamma rays. The positron excess, on the other hand, could stem from nearby astrophysical accelerators, perhaps young pulsars or supernova remnants that naturally spit out positrons. To date, no indirect signal can be clearly attributed to dark matter without alternative explanations. The indirect search is still very much alive, however. New telescopes and detectors with greater sensitivity are continuously scanning the skies. For example, the Cherenkov telescope array, currently under construction, will probe high-energy gamma rays with unprecedented precision and could potentially confirm or refute hints like the galactic center excess. Likewise, planned cosmic ray observatories and X-ray telescopes may sharpen the picture of those positron and X-ray anomalies. Until something is confirmed beyond doubt, the indirect approach remains a waiting game, watching the universe for any strange fireworks that might hint at dark matter interactions. If the listening strategy on Earth is to sit patiently in a quiet room, the contrasting strategy in space is to watch for any hint of cosmic fireworks. Both approaches so far have kept us in suspense. Interesting hints, but nothing conclusive. That leaves the third strategy. Instead of waiting for dark matter to come to us, why not try to make it ourselves? In contrast to the calm, patient search underground, or the vigilant gaze at the heavens, the collider approach is like deliberately crashing symbols together and scanning for a hidden melody in the ensuing chaos. This is the approach of the particle accelerators. The collider searches for dark matter. It's a dramatically different tactic, loud, energetic, and explosive, yet complementary to the quiet approaches we've seen. The principle behind collider searches is simple. Instead of waiting for dark matter to drift by, produce it in a high-energy smash-up of known particles. Einstein's famous equation, E equals mc squared, tells us that energy and mass are two sides of the same coin. Energy can transform into particles of matter, given enough concentration. In a powerful collider, we accelerate particles, usually protons or electrons, to near light speed and then let them slam into each other. In those tiny, fierce collisions, the kinetic energy concentrates and can crystallize into new, massive particles that weren't there before, if physics permits their existence. In fact, the early universe itself was a kind of colossal natural collider. In the intense fireball just after the Big Bang, particles of all kinds, possibly including dark matter, were being forged in energetic interactions. By recreating a tiny slice of those conditions in the lab, we hope to summon similar exotic particles into existence now. High-energy collisions have historically been our gateway to discovering new particles. Nearly every fundamental particle known, from quarks to the Higgs boson, was first seen as a blip in the debris of a particle collision. It is only natural to extend this approach to dark matter as well. At CERN's Large Hadron Collider, LHC, the world's most powerful particle accelerator, protons race through a 27-kilometer circular tunnel at almost light speed, guided by powerful superconducting magnets. They collide head-on inside gigantic detectors such as ATLAS and CMS, recreating miniature fireballs of primordial energy. Each of these detectors is colossal, about the size of a 5-story building, and packed with layers of sophisticated sensors to track and measure the spray of particles from every collision. Thousands of particles can burst forth from a single proton-proton collision, most of them the well-known fragments of subatomic shrapnel that quickly decay into showers of lighter particles. Amid this subatomic fireworks show, any dark matter particles produced would be peculiar in that they leave no trace in the detector. They would fly out of the collision point like invisible phantoms. However, what can be noticed is their absence. Momentum must be conserved in the collision. If you add up all the visible particles' momenta after a collision and find something missing to balance the books, that missing momentum might have been carried away by an undetected particle. In practice, researchers look for events where something visible recoils as if struck by an invisible partner. For example, one classic collider signature is a single jet of particles shooting off in one direction with no balancing jet on the opposite side, as if an unseen entity took recoil in the other direction. The detectors measure a significant momentum imbalance, signaling that some momentum vanished, presumably with a particle that the detector didn't see. Such events aren't particularly rare, because neutrinos, produced in many ordinary processes, also leave the detectors invisibly and can cause imbalances. The challenge is to sift through an enormous number of collision events and find an excess or a pattern in those missing momentum events that can't be explained by neutrinos or any known process. Physicists compare what they observe with detailed predictions of the standard model, the well-established theory of particles, to see if there are any deviations hinting at new particles. So far, the LHC's results in these searches have been consistent with standard model expectations. In other words, we haven't found an unexplained surplus that would point clearly to dark matter. If a discovery comes, it might not be a dramatic bump or a single event, but rather a subtle statistical bump in the distributions of missing energy or other properties that gradually stands out with enough data. One major theoretical framework that guided many collider searches is supersymmetry. As mentioned, supersymmetry predicts a host of new particles, including an excellent dark matter candidate, the lightest neutralino. If supersymmetry is realized in nature, and within the LHC's energy range, the collider might produce these new particles. They would often decay in chains, ending with the neutralino, which would escape as dark matter. Early on, there was hope the LHC would see a whole cascade of new particles, a spectacular confirmation of supersymmetry and dark matter in one swoop. By the end of its second run, after many years of data taking at high energies, the LHC had not found any of the predicted supersymmetric particles in the ranges it was sensitive to. This doesn't kill supersymmetry outright. The superpartners might simply be heavier or more subtle than anticipated. But it has certainly put that theory on shaky ground. The neutralino, once the leading WIMP candidate backed by theoretical elegance, remains a phantom lurking impossibility. Still, the LHC has achieved great things, notably the discovery of the Higgs boson, a milestone in 2012, and for a time, many hoped dark matter would soon follow. The absence of any obvious new particles in the LHC data was a reality check. It reminded physicists that nature often guards her secrets tightly. Rather than a quick victory, the search at colliders became a long-term campaign. The Atlas and CMS teams refined their analyses, scrutinizing every nook of the data for subtle deviations that might hint at dark matter. They also began planning upgrades and even future colliders, driven by the belief that a signal could still lie at energies just beyond our current reach. However, the search at colliders is far from over. The LHC is now undergoing upgrades to increase its collision rate and energy reach. The high luminosity LHC will collect an order of magnitude more data in the coming years, which will improve sensitivity to rare processes. Physicists are also exploring innovative search strategies. Instead of looking only for the simplest missing energy events, they're considering more complex signatures. For instance, scenarios where a dark particle might cause a track to disappear in the detector, as in some supersymmetry models with long-lived charged particles that decay invisibly, or looking for unusual combinations of known particles that could indicate a mediator of dark matter. Meanwhile, new collider projects are being proposed that could further extend our reach. Concepts like a future circular collider at CERN or a next-generation linear collider are partly motivated by the desire to pin down dark matter's particle nature, if the LHC cannot. The collider approach highlights another important facet of the dark matter hunt: synergy. If one day a collider produces a possible dark matter particle candidate, say we see an imbalance that strongly suggests a new particle is flying off, unseen, that alone wouldn't be conclusive proof of cosmic dark matter. We'd have to link it to what astronomers observe. Conversely, if a direct detection experiment in a lab or a telescope in space finally gets a clear dark matter signal, colliders would then be crucial for studying that particle in detail, by producing it on demand and measuring its properties. In essence, the different search methods complement each other. A true discovery might require catching dark matter's effects in multiple ways: hearing its whisper in an underground detector, seeing its shadow in the sky, and creating it for examination in a collider. Scientists often say they would be most convinced dark matter is solved when evidence from cosmology, direct detection, and colliders all point to the same solution. As we stand in the mid-2020s, surveying the landscape of the dark matter quest, we find ourselves at a tantalizing crossroads. We have chased the leading candidates: WIMPs, neutralinos, axions, with great ingenuity and persistence. We have ruled out many possibilities and sharpened our techniques to unprecedented precision. Yet the prize remains elusive. The universe has not yielded its dark secret easily. This has prompted some to consider more radical ideas and to question long-held assumptions. Could it be that our very premise, that dark matter is some particle, is incomplete or incorrect? A few researchers have explored the idea of modifying gravity itself as an alternative to dark matter, proposing that perhaps the laws of gravity change on galaxy scales. Such theories are known as MOND or TVS. So far, these alternative gravity models haven't been able to explain the full range of observations as successfully as dark matter does. But the ongoing absence of a particle detection ensures that such discussions remain on the table. What we can say for certain is that dark matter is a central piece of the cosmic puzzle. It influenced the formation of galaxies and clusters. It affects how those galaxies rotate and how light travels through the universe. And it appears to be an indispensable ingredient in our best cosmological models. Uncovering its identity will not only solve a decades-old mystery, but also open a new window into the fundamental workings of nature, potentially revealing new particles, forces, or principles that extend our current understanding of physics. The quest for dark matter is far from over. Each approach, from the silent vigil of direct detectors to the wide-eyed observation of the sky, to the high-energy collisions at colliders, adds a vital piece to the puzzle. It has become a saga of science, a tale of bold proposals, painstaking experiments in deep silence and high-energy chaos, and the resilience of researchers who refuse to give up. Each setback or null result only spurs new ideas and sharper questions. After decades of chasing shadows, scientists remain as determined as ever, knowing that to find dark matter would be to unveil a fundamental truth about the cosmos. The story of dark matter remains one of persistence and wonder, and it is still being written. All across the universe, galaxies like our own Milky Way are cradled by something we cannot see. Enveloping each galaxy is a vast, invisible halo of dark matter, a hidden mass that extends far beyond the galaxy's glowing stars. This dark halo is often compared to a kind of cosmic scaffold or skeleton, an unseen framework holding the galaxy together. Within its embrace, stars orbit at startling speeds, even the ones at the outskirts, where ordinary gravity from visible matter alone would be too feeble to keep them bound. Yet the galaxies do not fly apart. It is the gravity of this dark matter halo that provides the extra glue, silently supporting the structure of the galaxy. Decades ago, astronomers first realized the need for these invisible halos when they mapped how fast stars and gas move in galaxies. In galaxy after galaxy, they found a puzzling pattern. The stars far from the center were moving just as fast as those closer in. According to Newtonian gravity, stars on a galaxy's edge should orbit more slowly if only the visible mass is pulling on them. But instead of slowing down, the outer stars keep up their speed. It was as though an additional hidden mass surrounded the galaxy, adding gravitational pull. This was one of the first clues that a huge amount of unseen matter, dark matter, encircles each galaxy, far outweighing the stars within. In our Milky Way, for example, the stars, gas, and dust we see are just a small fraction of its total mass. The dark matter in the Milky Way's halo is thought to be at least 10 times more massive than all the ordinary matter in the galaxy. And this halo is enormous. It stretches well beyond the luminous spiral arms, hundreds of thousands of light years into space. Imagine the bright disk of the Milky Way as a sparkling city at night, and around it, an invisible countryside of dark matter extending far beyond the city lights. We cannot see this dark landscape, but its gravitational influence is unmistakable. It keeps our galactic city intact. This hidden halo is not a static backdrop. It actively shapes the life of a galaxy. The dark matter's gravity affects how a galaxy rotates, and even how it was born. Long ago, before our galaxy formed, a clump of dark matter had already started drawing in ordinary gas, providing a deep, gravitational well where stars could begin to form. Every galaxy is thought to have started this way, forming at the center of a denser lump of dark matter. In this sense, dark matter came first, creating wells of gravity that served as nurseries for galaxies. Without that initial scaffold of dark matter, the gas might never have condensed so quickly into the galaxies we see today. Dark matter halos also guide how galaxies grow over time. Galaxies often collide and merge, and when they do, it is their dark halos that feel each other's pull first. A smaller galaxy approaching a larger one is captured by the big galaxy's dark matter halo, long before the stars and gas directly interact. The halos merge, swirling together, and eventually the galaxies themselves coalesce. Over billions of years, this process, driven largely by dark matter gravity, builds up ever larger galaxies from smaller ones. Our own galaxy likely feasted on smaller companions in the past, pulling them in through its halo's gravitational influence. The remnants of those events can still be seen as streams of stars orbiting the Milky Way, marking where dwarf galaxies were torn apart by our galactic halo. Even when a galaxy is isolated, its dark matter halo is a dynamic environment. Stars occasionally get flung out into the far reaches of the halo through interactions, becoming lone wanderers bound by dark matter's pull. Clouds of gas can also extend far into the halo, sometimes raining back down onto the galaxy and sparking new star formation. All of these processes are governed by the halo's invisible hand. The ordinary stars and nebulae are like leaves moving in a breeze, and the dark halo is the air itself, transparent yet constantly influencing every motion. Though we cannot observe dark matter directly, we have developed ways to map these halos. One method relies on the phenomenon of gravitational lensing, where the gravity of a massive object bends the path of light. A galaxy's dark matter halo, despite being invisible, has mass, and thus bends light from more distant galaxies that lie behind it. Astronomers have observed subtle distortions in the shapes of background galaxies, a cosmic optical illusion that lets us infer the presence of a massive halo in the foreground. By carefully analyzing these distortions, we can create a kind of contour map of dark matter around galaxies. These maps confirm that the halos are vast and massive, often much more extensive than the galaxy's visible stars, and roughly spherical in shape, like a gigantic unseen cloud around the galaxy. They reveal that dark matter halos extend far beyond the last visible star of a galaxy, encompassing a region much larger than one might guess from starlight alone. In a sense, the galaxy sits deep inside this huge cushion of invisible mass. In effect, each galaxy sits in the center of an enormous ball of dark matter, a ball that has no sharp edge, but gradually fades outward. It truly is a galactic skeleton, a supportive frame that the galaxy's structure hangs upon. The luminous spiral arms, the glowing core, the twinkling halo of star clusters, all of these visible components are nestled inside the dark halo that envelops them. The concept is awe-inspiring. Most of the matter of a galaxy is not the brilliant stars or glowing nebula we see, but this dark, transparent mass orchestrating the galaxy's behavior from behind the scenes. As we deepen our understanding of these halos, new questions arise. What is the exact shape of the dark matter halo of our Milky Way? Is it perfectly spherical, or stretched and squashed by past collisions? How far does it extend, and does it have lumpy substructures of its own? Astronomers are searching for answers, for instance by studying streams of stars that act as tracers of the halo's gravitational field. These stellar streams, leftovers of smaller galaxies that the Milky Way tore apart, ripple through our halo. By observing their motions, scientists can infer where dark matter is concentrated, almost like feeling the shape of an invisible sculpture by tracing your hands along its surface. Early indications suggest the halo may not be perfectly smooth. It could have clumps or an irregular shape, hinting at a complex history of mergers. These explorations show that a galaxy's dark matter halo is not a simple, featureless blob. It has a rich inner life shaped by cosmic events. It holds the imprints of everything the galaxy has absorbed or interacted with. When a small galaxy merges into a larger one, its dark matter adds to the halo and can create subtle density ripples. When two galaxies of similar size collide, their halos pass through each other and oscillate, setting off waves that can persist for eons. The galaxy's visible stars eventually settle into a new arrangement, but the halo remembers, preserving a record of the encounter in its diffuse density patterns. Thinking of dark matter halos in this way, we begin to appreciate them as active components of galaxies, not just passive containers. They define the gravitational landscape in which a galaxy lives. They are the scaffolding upon which the visible galaxy is built, and they continue to direct its fate through gravity's persistent tug. In the grand scheme, each halo is like a single cell in the body of the universe, with galaxies as the nucleus. And just as cells connect to form larger structures, these halos link up along an even larger framework, the cosmic web. With the halos of individual galaxies in mind, our journey now moves outward to an even larger scale of dark matter's influence. We now drift outward, far beyond the scale of a single galaxy, and behold the universe on its grandest scales. What emerges is an astonishing pattern. Galaxies are not scattered randomly like isolated islands, but instead arranged in immense filaments and sheets, with vast empty voids between them. It is as if the galaxies trace out a cosmic web, a lattice of matter spanning across the cosmos. Enormous clusters of galaxies sit at the junctions of these filaments, while tendrils of galaxies and gas stretch between them like bridges. And in between, there are gargantuan voids, regions spanning tens of millions of light years that contain hardly any galaxies at all. Cosmic deserts, separating the busy intersections of the web. This large-scale design is not a random accident. It is the inevitable outcome of gravity shaping matter over billions of years, and dark matter is the primary architect of this cosmic tapestry. In the very early universe, matter was almost uniformly spread, with only tiny irregularities, slightly denser spots sprinkled through the nearly even mix. Those small variations were enough for gravity to gain a foothold. Regions that started off just a bit denser exerted a stronger pull on their surroundings. Dark matter, invisible yet dominant, began to clump in those zones. As time went on, the denser clumps drew in more and more material, growing into elongated strands. Ordinary matter, gas that would later form stars, was pulled along, falling into the gravity wells carved out by the dark matter. Over epochs, this process sculpted an intricate network of filaments and voids, the cosmic web. Imagine being able to see this web in its entirety. You would observe something akin to a vast, three-dimensional spider web, or the neural network of a giant brain. The threads of the web are the dark matter filaments, mostly invisible but holding immense mass. Galaxies shine like tiny beads strung along these threads, concentrated where the filaments intersect in brilliant clusters. The empty gaps, the voids, appear as great black holes in the pattern, not because they contain black holes, but because they lack the stars and galaxies that would light them up. In reality, even those voids are likely filled with tenuous dark matter, but far less than in the dense filaments. Hence they host few galaxies. For all the grand beauty we see in the galaxies, the true bulk of the cosmic architecture remains dark and unseen, revealed only by its gravitational pull. One might call dark matter the universe's skeleton or backbone, and the cosmic web is that skeleton made manifest. The filaments of dark matter are the invisible highways along which matter flows. Galaxies and galaxy clusters form where these highways cross, much as towns and cities often form at crossroads. Gravity guides this growth. Dark matter's pull channels gas into the filaments, funneling it into the developing galaxies along the way. This means that galaxies are fed by the cosmic web. They draw in fresh gas that can ignite new generations of stars. Likewise, whole galaxies travel along the filaments, gradually sliding toward the gravitational centers at the nodes. In this manner, galaxy clusters grow larger, as filaments feed them both matter and galaxies over time. Observations have confirmed this grand design. As technology advanced, astronomers began to map the positions of tens of thousands, then millions of galaxies. In the late 20th century, redshift surveys, three-dimensional maps of galaxy locations in space, revealed gigantic structures, walls and filaments stretching across hundreds of millions of light-years. One famous example was dubbed the Great Wall, a sheet-like arrangement of galaxies so large it defied imagination. These observations were stunning, but they matched what cosmic theorists had predicted would happen if dark matter filled the universe. Computer simulations that included dark matter had long been showing the formation of a similar cosmic web. The agreement between what simulations predicted and what telescopes eventually saw was a triumph for the dark matter theory. Because dark matter makes up the bulk of the mass, the cosmic web is fundamentally a dark matter structure. The luminous galaxies merely highlight a pattern that was woven by invisible hands. Roughly 85% of the matter in the universe is dark matter. So when we gaze upon the cosmic web through galaxy surveys, we are really seeing just a small luminous fraction of a much larger dark framework. In a sense, our maps of galaxies are like seeing the twinkling lights of distant cities at night and inferring the existence of the connecting roads and landforms we cannot see in the dark. The galaxies tell us where the mass concentrations are, but not all of that mass is visible. We know from gravitational effects that far more matter resides in and around those galaxies and filaments than the eye can see. Another powerful way we probe the cosmic web is through gravitational lensing on large scales. Just as an individual galaxy's dark halo can bend light, so too can an entire filament or cluster of dark matter. By observing the distorted shapes of distant galaxies behind these massive structures, astronomers can map out where the dark matter lies on cosmic scales. Indeed, gravitational lensing studies have successfully detected and mapped filamentary structures of dark matter bridging between galaxy clusters. In one remarkable case, the Hubble Space Telescope helped chart a filament of dark matter and galaxies feeding into a distant cluster, essentially observing the cosmic web in action. The map showed matter streaming along a 60 million light-year-long filament into the cluster, confirming that these strands are channels of material flowing into the densest regions. It offered a striking confirmation that filaments do indeed funnel matter into clusters, as scientists long suspected. This was direct, visual evidence that the cosmic web is a physical reality and not just a feature of simulations. Even more recently, astronomers captured the faint glow of gas in a filament of the cosmic web directly. Using a sensitive instrument on a large telescope, they observed a colossal filament stretching millions of light years, glowing as it connected two young galaxies in the early universe. This image, one of the most detailed of the cosmic web ever taken, offered a first-hand glimpse of the bridges that connect galaxies. It is a striking confirmation that the cosmic web is not just a theoretical construct or a simulation artifact, but a physical reality that can be observed, given enough sensitivity and time. Within the filaments, gas flows can be thought of as cosmic rivers. That gas streams into galaxies, feeding star formation and growth. Meanwhile, galaxies themselves can migrate along the filaments, gradually heading toward the massive cluster nodes. At the intersections, where filaments converge, gravity has piled up huge reservoirs of dark matter and gas, which have cooled and condensed into swarms of galaxies. These nodes are the galaxy clusters and superclusters, the most massive structures in the universe held together by gravity. When clusters grow extremely large, they themselves become nodes connected by filaments. So even clusters are part of this web, not isolated objects. Conversely, in the voids between filaments, the scarcity of dark matter means little gravitational pull to gather gas or form stars. Galaxies in voids are few and far between. One of the most striking examples is the Boötes void, a spherical region hundreds of millions of light years across that contains almost no galaxies. Those few galaxies that do exist in such a void often find themselves marooned, with little fresh material to fuel new stars. Life in a cosmic void is isolation on the grandest scale. The cosmic web is an evolving structure. What we see today is the result of billions of years of cosmic history, and the web continues to evolve. Clusters will keep growing as they pull in more galaxies and gas. Filaments may thin out as their material is drained into clusters, or they may merge with other filaments. Void spaces might expand as matter evacuates them further. Our universe, in its expansion, stretches this web as well. But gravity fights against pure expansion locally by pulling things into the web's dense strands. There is a continual tension between the expansion of the universe and the drawing together of matter via gravity. Dark matter, being the dominant gravitating mass, is at the heart of this cosmic tug-of-war, slowing expansion in some areas to form structure, even as space as a whole expands. Standing back and contemplating the cosmic web is humbling. We realize that our entire galaxy, with its hundreds of billions of stars, is just a tiny speck on one filament of this immense web of matter. The Milky Way, along with the Andromeda Galaxy and a few dozen smaller galaxies, resides in a filament that feeds into the Virgo cluster, the nearest galaxy cluster. That local context is our cosmic address on the web. It underscores that galaxies are not solitary. They are part of a larger arrangement dictated by dark matter's gravity. The picture of the cosmos as a web also underscores how crucial dark matter is. Without it, such coherent patterns of structure likely would never have formed. Normal matter alone, interacting with light and radiation, would have stayed more smooth and uniform for much longer, perhaps delaying galaxy formation well past the point we observe it. Dark matter gave the universe the backbone to form structure early and quickly. Having seen how dark matter underpins the vast cosmic web, we can appreciate the scale of dark matter's influence. From holding individual galaxies together to connecting clusters across millions of light years. Yet, even on smaller scales, dark matter's effects can be puzzling. If we zoom in again, down from the scale of superclusters to the scale of the tiniest galaxies, we encounter some of the most intriguing and challenging clues about dark matter's nature. Our journey now turns to those dwarf galaxies and satellite systems, the little companions and fragments that orbit larger galaxies, for they hold secrets that sometimes defy our expectations. If the cosmic web shows how dark matter shapes the universe at the largest scales, dwarf galaxies reveal how dark matter behaves on the smallest galactic scales. Dwarf galaxies are tiny, faint collections of stars, sometimes only a few thousand or a few million stars, often found orbiting larger galaxies like the Milky Way. To the eye, they are unimpressive smudges of light, but what they lack in visible grandeur, they make up for in dark matter content. In many dwarfs, the stars are just the tip of an iceberg, accounting for only a minuscule fraction of the galaxy's mass. The rest, by all indications, is dark matter. Some of the ultra-faint dwarf galaxies discovered in recent years are so dominated by dark matter that over 99% of their total mass is invisible. In these diminutive galaxies, the few stars present are merely tiny beacons tracing the shape of an enormous dark halo. For all intents and purposes, these galaxies are almost entirely made of dark matter, with just a faint sparkle of starlight to mark their presence. Because dwarf galaxies have so little normal matter, they become exquisite test beds for our theories of dark matter. With virtually no bright gas clouds or star clusters in the way, the motions of the stars in dwarfs are governed almost entirely by dark matter's gravity. By studying how these stars move, how fast they orbit, and how their speeds change from the center of the dwarf to its outskirts, astronomers can infer the distribution of dark matter within. And here is where some puzzles arise. The smallest galaxies sometimes don't behave exactly as the simplest dark matter models would predict. These discrepancies between observation and theory on small scales have been a persistent challenge, one that has even been dubbed the small-scale crisis of the cold dark matter model. This small-scale crisis actually encompasses a few related puzzles that have kept astronomers busy for years. One long-standing issue is known as the missing satellites problem. Early computer simulations of cosmic structure suggested that a galaxy like the Milky Way should be surrounded by hundreds of small dark matter clumps, halos that, in theory, could host dwarf galaxies. Yet, when astronomers looked for dwarf galaxies around the Milky Way, they initially found only a few dozen. It seemed as though the simulations were predicting far more satellites than we actually observe. Where were all those missing dwarfs? For a time, this gap between prediction and observation was stark, leading some to question whether our understanding of dark matter was incomplete. Over the past decade or two, however, the gap has been narrowing. Deeper surveys of the sky have uncovered many more faint dwarf galaxies hiding in the darkness. These ultra-faint satellites are extremely hard to detect. Some have only a few thousand stars spread over a large area. But new instruments and techniques have brought them to light. Each discovery adds another point toward closing the tally. It now appears that the Milky Way does have a multitude of satellite galaxies, as simulations predicted, but many are so small and dim that we had missed them until recently. In fact, ongoing and upcoming sky surveys, like those to be conducted by the Vera C. Rubin Observatory, are expected to reveal even more of these elusive companions. By the time all are found, the Milky Way's entourage of dwarf galaxies may very well match the swarm of dark matter halos that simulations envision. That said, the missing satellites problem isn't entirely put to rest. While the Milky Way's count of dwarfs has grown, some other galaxies still show discrepancies, and details remain to be sorted out. It's possible that many of the predicted small halos are indeed there, but contain no stars at all, making them effectively invisible. So the puzzle persists in some cases, indicating that we may still be missing pieces of the story. Dwarf galaxies only form if enough gas cools and condenses to make stars in the first place. Tiny halos might simply never acquire that gas. And if a small halo manages to form a dwarf galaxy, it may not last forever. Such a galaxy can be quickly eaten by the larger galaxy it orbits. Indeed, small galaxies that fall into the Milky Way or Andromeda can get torn apart by gravitational tides. Their stars are stretched into faint streams and their dark matter halos dispersed. In this way, some satellites may effectively vanish from sight, contributing to the missing count. Thus, the apparent shortfall of observed dwarfs might not indicate a fundamental problem with dark matter at all, but rather the complexity of galaxy formation and survival in the shadow of giants. Another puzzle arises when we look at how dark matter is distributed in the cores of dwarf galaxies. Simulations, using the standard cold dark matter theory, often produce a very steep concentration of dark matter toward the centers of halos, a sharp peak or cusp of density. However, when astronomers measure the mass distribution in actual dwarf galaxies, they sometimes find that the dark matter is spread out more evenly in the inner region, forming a relatively flat core of constant density rather than a sharp cusp. This discrepancy between simulated halos, cusp-like, and observed dwarfs, core-like, is known as the cusp core problem. It's as if the real dwarf galaxies have a softer center than the pure dark matter models would suggest. There are several ideas for why this might be. One explanation points to the effects of normal matter. Though dwarfs have little of it, what they do have could still make a difference. Consider a young dwarf galaxy forming stars. If many of those stars explode as supernovae around the same time, they could push gas out from the center of the dwarf in a powerful burst. That sudden mass loss could weaken the gravitational pull in the center and allow the dark matter to drift outward slightly, turning a sharp cusp into a flatter core. Over billions of years and repeated episodes of star formation and gas ejection, a dwarf galaxy might systematically reshape its inner dark matter profile. In this way, the once cuspy dark matter distribution could be puffed out into a core due to the violent feedback from star formation. On the other hand, it's also possible that something about the dark matter itself is different than the simplest assumption. The standard theory treats dark matter as cold, moving slowly, and collisionless. Dark matter particles rarely, if ever, interact with each other, except via gravity. But what if dark matter particles can collide or scatter off one another a bit? Or what if they move slightly faster, so-called warm dark matter? Such variations in dark matter's properties could naturally create cores in small halos or reduce the number of tiny clumps. For instance, if dark matter particles scatter, the central density might spread out, solving the cusp issue, and if they are fast-moving, they might not clump as readily on small scales, potentially reducing dwarf numbers. These alternatives are speculative, but researchers are actively testing them against observations. So far, none of these modifications has conclusively replaced the standard cold dark matter model. But the fact that they are considered highlights how dwarf galaxies have pushed scientists to think hard about what dark matter is and isn't. Future observations of these tiny galaxies will help reveal whether such exotic tweaks are truly needed, or if the standard dark matter model can pass all the tests after all. One more small-scale conundrum has been nicknamed the too big to fail problem. Simulations of the Milky Way's dark matter halo predict not only a plethora of small subhalos, but also that a few of those subhalos should be relatively massive enough that they would naturally form plenty of stars and be visible as some of the brightest dwarf companions. These hefty satellites would be, in essence, too big to fail to become galaxies. Yet when we look at the actual dwarfs around the Milky Way, the brightest ones do not seem to correspond to the most massive subhalos predicted by simulations. Where are those massive subhalos hiding? If they have no visible counterparts, it suggests they failed to form stars despite their size. Or again, perhaps our models need subtle tweaking. It's possible that even these too-big-to-fail halos were stripped of their gas long ago by the Milky Way's gravity or blasts of radiation, effectively starving them of the material needed to form stars. Another possibility is that our simulation-based estimates of subhalo masses need refining once we include all the complexities of baryonic physics. For example, the gravitational influence of the Milky Way's own disk might disrupt some subhalos, preventing them from accumulating stars. As simulations grow more sophisticated and include such effects, some of these discrepancies may disappear. Indeed, improved models that incorporate the messy reality of star formation, supernova feedback, and interactions with big galaxies can produce satellite populations that look much more like what we observe. Curiously, just to complicate the picture, astronomers have even discovered a few galaxies that seem to have almost no dark matter at all. One example, identified in 2018, was a faint, diffuse galaxy whose star's motions indicated it could be almost entirely lacking in dark matter. This was a shocking finding. It's as if the skeleton were missing from one part of the body. How could a galaxy form or survive without the glue of dark matter? Some scientists suspect such galaxies might be extreme cases that formed in special ways, perhaps flung out of larger galaxies or stripped of their dark matter by tidal encounters. If the measurement holds up, and it's still being debated, it oddly doesn't refute dark matter's existence. Instead, it suggests that under rare circumstances, a galaxy can lose its dark matter. In an indirect way, that's yet another clue. It shows dark matter can behave as a separate component, not inevitably bound to all collections of stars. These 1-in-a-million galaxies without dark matter are puzzling, but they only underscore the rule by highlighting the exception. Despite these challenges, the dark matter paradigm still provides a successful overall framework. The small-scale puzzles have not overthrown the concept of dark matter. Instead, they have driven it to evolve. They remind us that galaxy formation is a complex interplay of dark matter and ordinary matter. Dwarf galaxies, being on the cosmic fringes, accentuate that interplay in ways we're still working to fully understand. Each new faint galaxy we discover, and each detailed measurement of a dwarf's rotation or velocity dispersion, adds a piece to the puzzle. In many cases, the discrepancies are shrinking as data improve and models get refined, but a whiff of mystery remains. These tiny galaxies have become a crucial proving ground for cosmology. In their dim light, we test the limits of our theories. So far, nothing we've seen in dwarfs definitively breaks the dark matter model. The fact that we have to account for things like feedback from stars or consider exotic dark matter properties shows how nuanced the full picture is. In science, such tension between prediction and observation is where we often learn the most. The dark matter theory has had to face these small-scale stress tests, and from them we gain a deeper understanding of both dark matter and galaxy formation. While dwarf galaxies quietly challenge us, other cosmic events shout their message about dark matter loud and clear. If you want striking, visual evidence of dark matter's presence, you won't find a better example than the aftermath of a colossal galactic collision. And so, we turn our attention from the smallest galaxies to one of the most dramatic scenes in the universe. The Bullet Cluster, a cosmic crash that offered a stunning confirmation of the existence of dark matter. Picture two immense clusters of galaxies barreling toward each other in the depths of space. Each cluster is a colossal collection of galaxies, hot gas, and dark matter, bound together by gravity. When they collide, it's not like a simple car crash. It's more like two clouds passing through one another. The individual galaxies, separated by vast distances, mostly slip past each other without direct hits. The hot gas in the clusters, however, does collide. As the clusters merge, their gas clouds slam together, heating up even more and slowing down, like two people running into each other and coming to a stop. The dark matter, on the other hand, behaves quite differently. Being effectively collisionless, the dark matter in each cluster just cruises through the collision, hardly breaking stride. This creates a peculiar situation. The contents of the clusters become separated by type. The gas ends up stuck in the middle, while the galaxies and dark matter sail ahead and keep going. This isn't just a theoretical scenario. Astronomers have observed it happening. One of the most famous examples is called the bullet cluster. It's actually a pair of galaxy clusters in the process of colliding, about 3.8 billion light-years away from Earth. In images of the bullet cluster, you can see the aftermath of the cosmic wreck. X-ray telescopes show a bright cloud of superheated gas that has been left behind in the collision's wake. This gas used to reside in the two separate clusters, but when the clusters crashed together, the gas interacted and was stripped out, piling up in the middle. Meanwhile, the galaxies from each cluster have essentially passed through the collision and continued on their way. They now lie ahead of the gas cloud, beyond the collision region. And crucially, those galaxies did not go alone. They are accompanied by the bulk of each cluster's dark matter. In effect, the galaxies carried with them most of the cluster's mass, invisible but present. How do we know where the dark matter went? After all, we cannot see it directly. The clue comes from gravity itself, via an effect known as gravitational lensing. The bullet cluster is massive enough that its gravity bends the light from more distant background galaxies, distorting their images into arcs. By carefully analyzing these lensing distortions, astronomers can map the distribution of mass in the cluster, much like inferring the shape of an invisible object by the pattern of light it distorts. When they did this for the bullet cluster, the results were striking. The mass was concentrated around the clumps of galaxies, not around the clump of gas. In other words, most of the matter in the cluster pair had moved ahead with the galaxies and not with the colliding gas. To visualize the scene, astronomers often present a composite image of the bullet cluster with different colors highlighting different components. The hot gas, mapped by X-ray observatories, glows in one hue and lies in the middle. The total mass distribution, mapped by gravitational lensing, is shown in another hue and sits around the galaxy clumps on either side. The separation is plain to see. The mass, most of it dark matter, is offset from the normal matter, the gas. In fact, in galaxy clusters, the majority of the ordinary mass is in the form of that hot gas. So if dark matter were not present, the center of mass should line up with the gas. But in the bullet cluster it doesn't. This cosmic collision created a natural experiment that cleanly separates the unseen mass from the seen. It's worth noting how the bullet cluster got its name. One cluster's core has shot through the other's body of gas, generating a distinct shock front in the X-ray cloud that looks like a bow shock from a supersonic bullet. That smaller cluster is effectively the bullet piercing through. The relative speed of this collision is breathtaking, on the order of thousands of kilometers per second. Such extreme events are rare, but they offer an invaluable opportunity to witness physics that would otherwise be hidden. When the bullet cluster findings were announced in the mid-2000s, they made a huge splash. Media headlines even called it direct proof of dark matter. While scientific caution avoids declaring absolute proofs, it's safe to say the bullet cluster delivered one of the most compelling pieces of evidence to date that dark matter is real and distinct from normal matter. This observation is a smoking gun piece of evidence for dark matter. It shows that whatever most of the mass in those clusters is, it does not interact via gas pressure or electromagnetism. It doesn't slow down when the gas slows down. It behaves exactly as dark matter was predicted to, racing through the collision unaffected, solely influenced by gravity. The bullet cluster basically gave us a cosmic experiment. It separated the visible matter, the gas, from the gravitational mass. The visible matter got stuck, but the gravitational mass did not, meaning the gravity wasn't coming primarily from the visible matter. Something else, something dark, was carrying that mass. Alternative explanations to dark matter have a very hard time with this scenario. If there were no dark matter and only modified gravity, one would expect the gravity to be anchored where the ordinary matter is, in the big gas cloud. But in the bullet cluster, the gravity, as revealed by lensing, is clearly offset from the ordinary matter, concentrated around the galaxies that have moved on. This is extremely difficult to explain without some form of unseen mass. The bullet cluster, along with a few other similar cluster collisions observed since, has been a crucial exhibit in the case for dark matter. It's one thing to infer dark matter from galaxy rotation curves or general cosmic patterns. It's another to see its effects plainly diverging from normal matter in the sky. For many scientists, the bullet cluster was the aha moment that solidified dark matter's reality. After witnessing such a cosmic demonstration, there remained little doubt among astronomers that dark matter is real. Yet even with such compelling evidence, we are still left with the challenge of understanding dark matter itself. Knowing it's out there is one thing. Figuring out what it is another. Thus, the quest evolved from simply demonstrating dark matter's existence to determining its nature, a task that required new approaches. To bridge that gap, scientists often turn to a powerful tool: simulations. By recreating the universe inside a computer, they can test whether our dark matter theories truly produce a cosmos like the one we observe, and explore the subtle consequences of different dark matter ideas. This next step in our journey takes us into the realm of these cosmic simulations, where darkness can be manipulated and examined in silico. Imagine being able to rewind and replay the history of the universe, or even to tweak its ingredients to see what happens. This is essentially what scientists do with cosmological simulations. Using powerful supercomputers, they create a virtual universe governed by the laws of physics and whatever assumptions we have about dark matter. They start from the conditions of the early cosmos, a nearly uniform spread of matter with tiny ripples, and let gravity take over. In these digital universes, eons pass in a matter of hours or days of computing time. Dark matter particles clump and form halos, filaments stretch across space, and galaxies ignite within those dark matter wells. When the simulation concludes, the researchers can compare the virtual universe to the real one. Does it produce galaxies distributed in a cosmic web like we observe? Do the galaxies in the simulation have the same patterns of clustering and rotation as actual galaxies? By and large, if dark matter is cold and behaves as expected, the simulated universe does look remarkably like our own. This concordance between simulations and observations is a big success for the dark matter theory. Long before we had detailed maps of galaxies stretching to the horizon, simulations predicted that matter in the universe should form a web-like structure under gravity's pull. When large redshift surveys eventually observed the cosmic web of galaxies, it matched the patterns the computers had generated. For instance, early experiments with fast, hot, dark matter particles showed galaxies forming much later and more unevenly than observed, whereas the cold dark matter assumption produced much better agreement. Similarly, simulations of galaxy clusters showed that they should exhibit certain gravitational lensing signatures and substructures, and we find those in real clusters. The ability of simulations to foresee these things is a strong indication that our basic picture, with dark matter included, is on the right track. Simulations have also illuminated the small-scale puzzles that we encountered. For instance, by including the effects of stars and gas, the baryonic physics, in simulations, scientists can test whether feedback from supernova can indeed flatten a dark matter cusp into a core in a dwarf galaxy. In many cases, the simulations with vigorous star formation winds do create cores, suggesting that the cusp core problem may be solved by explosive feedback. Simulations have also shown that the presence of a large central galaxy can alter the fates of surrounding subhalos. Sometimes the Milky Way's disk and its tides can destroy would-be satellites or reduce their masses. When those processes are accounted for, the simulated number of satellites and their properties become more like what we observe, easing the missing satellites and too-big-to-fail tensions. In short, increasingly realistic simulations, those that include both dark matter and normal matter physics, tend to alleviate many of the discrepancies that appeared in simpler dark matter-only models. Another advantage of simulations is that they allow us to experiment with different dark matter hypotheses in a way we cannot with the real universe. If someone proposes a new kind of dark matter, say, particles that move faster or that can collide with each other, we can program those properties into a simulation and see what changes. Warm dark matter, for example, tends to blur out the smallest clumps. When simulations are run with warm dark matter, they produce fewer dwarf halos and more diffuse cores. Researchers can then compare these outcomes with actual data on dwarf galaxies to judge whether those alternative models perform better or worse than standard cold dark matter. So far, the cold dark matter model, with some help from normal physics, has continued to hold up well, but these exercises are valuable. They show us what particular observations, like the exact number and distribution of tiny galaxies, can tell us about dark matter's properties. Simulations aren't limited to structure formation on large scales. They also help in planning how to detect dark matter particles. For instance, certain simulations track not only where dark matter accumulates, but also where dark matter particles might annihilate each other if they are of a type that can self-annihilate, as some particle theories suggest. These predictions can tell astronomers where to look for faint signals, like gamma rays, that might come from rare dark matter interactions, for example, in the dense centers of galaxies or galaxy clusters. In fact, the center of our Milky Way emits an unusual glow of gamma rays that some scientists have noted could be a sign of dark matter annihilations. An intriguing possibility, though it's still uncertain and could have other explanations. While no definitive signal has been confirmed yet, simulation-guided searches continue, helping narrow down the possibilities. Perhaps one of the most compelling outcomes of simulations is how they let us visualize the invisible. Through them, we can see the dark matter distribution, the halos, filaments, and voids, in a way that no telescope can. These visualizations reveal a universe woven of dark matter clumps connecting in vast networks, making the cosmic web almost tangible. Such images have made the cosmic web concept something we can almost picture in our minds. As computers become faster and data sets richer, simulations are continually improving. In the late 1970s and 1980s, the earliest cosmological simulations could only handle a few thousand test particles, yielding very coarse results. By the mid-2000s, projects like the Millennium Simulation were tracing billions of particles, revealing the cosmic web's structure in unprecedented detail. Today, state-of-the-art programs, for example, the Illustris and Eagle simulations, go further by including gas physics and star formation, producing virtual galaxies that closely resemble those observed by our telescopes. Modern simulations include billions of particles, subtle physics of gas cooling, star formation, and even feedback from black holes. They have progressed from simple maps of dark matter to detailed virtual universes, where one can fly through galaxies and clusters that look strikingly real. And importantly, these simulations serve as a bridge between theory and observation. When a simulation tuned with certain dark matter properties fails to match what we see in the sky, it tells us something is off with the theory. In that way, the computer becomes a testing ground for dark matter ideas, letting us test different scenarios and see what reproduces the cosmos we observe. Yet, even the best simulation can only tell us so much. It can strengthen our confidence that our model of dark matter works, but it doesn't by itself reveal what dark matter actually is. Still, even the most sophisticated simulation cannot directly reveal the true identity of dark matter. That will require something more, a way to actually detect or explain this elusive ingredient of the cosmos. And while simulations have shown us how dark matter shapes the universe, some researchers wonder if there could be an entirely different explanation. Could we be mistaken in thinking there's something out there at all? This brings us to the bold alternative ideas that some scientists have proposed. Attempts to do away with dark matter by changing the laws of gravity instead. What if there are no dark matter particles at all, and we've been chasing a ghost? A number of physicists have asked this question and come up with alternative explanations for the phenomena attributed to dark matter. The most developed of these ideas involve modifying the laws of gravity. In essence, instead of assuming an unseen mass to explain why galaxies rotate as they do, these theories tweak the rules of motion so that galaxies can rotate faster without flying apart. The poster child of modified gravity is a hypothesis known as MOND, short for Modified Newtonian Dynamics, first proposed in the early 1980s. MOND posits that Newton's laws of gravity change behavior when the acceleration involved is extremely low, as is the case at the outskirts of galaxies. In the MOND framework, a star on the far edge of a galaxy feels a stronger effective pull than Newton's original laws would predict, causing it to orbit faster than expected without needing any dark matter. Remarkably, with a single mathematical adjustment, MOND can explain the general shape of rotation curves for many galaxies. For a time, MOND and its later extensions provided an enticing alternative. It could naturally account for the flat rotation curves of spiral galaxies, the very observation that first pointed astronomers toward dark matter. MOND even predicted a tight relationship between a galaxy's visible mass and its rotation speed, something called the baryonic Tully-Fisher relation, that has been observed in real galaxies. This seemed like a point in its favor. Perhaps gravity itself has nuances we hadn't understood, and those quirks remove the need for invisible matter. However, modified gravity theories face significant challenges. While they can be tuned to handle the dynamics of individual galaxies, they struggle to match the wealth of evidence for dark matter on larger scales. Galaxy clusters, for example, exhibit gravitational effects, like the high speeds of galaxies within them and certain gravitational lensing patterns, that are hard to reconcile without some form of unseen mass. The bullet cluster's collision, which we discussed, is particularly troublesome for MOND-like approaches. There, the gravity appears separated from normal matter in a way that tweaking gravity alone doesn't reproduce. Some MOND proponents have attempted fixes, such as adding a bit of unseen matter, like neutrinos, to the mix, but that essentially defeats the purpose of a no dark matter theory. Moreover, the success of the standard dark matter model in explaining the cosmic microwave background patterns and the large-scale structure of the universe is a high hurdle for modified gravity to clear. To make MOND work in a fully relativistic context, compatible with Einstein's general relativity and all the cosmological data, physicists had to construct more complex theories with additional fields or forces. One example was TeVeS, tensor vector scalar gravity, a theoretical framework that extended MOND into a relativistic form. These models can be quite complicated, and even then, they often still imply the existence of some unseen mass, or fail to explain certain observations as neatly as the dark matter hypothesis does. Apart from modified gravity, other unconventional ideas have been floated. In the early days of the dark matter debate, some wondered if the missing mass could simply be ordinary matter in hard-to-see forms. Planets, burnt-out stars, or black holes lurking in galactic halos, so-called MACHOS, massive compact halo objects. Extensive searches, however, found that such objects, while they exist, are nowhere near abundant enough to account for the missing mass. More recently, some theorists have explored concepts like emergent gravity, where gravity's behavior on cosmic scales arises from deeper quantum principles and mimics dark matter effects. These ideas are intriguing, but highly speculative, and they haven't yet provided a clear, testable replacement for dark matter. To date, no alternative theory has managed to explain the full sweep of observations, from the cosmic microwave background and galaxy clusters down to individual galaxies, as simply and successfully as the dark matter model does. For perspective, this dark matter hypothesis asks us to accept that about 5/6 of the universe's matter is in this invisible form, a bold proposition, but one that unifies phenomena from the early universe to the present day under a single explanation. Most astronomers and cosmologists remain convinced that dark matter, in some form, is real. Still, the willingness to challenge the paradigm is important. It reminds us that science progresses by considering multiple angles, and even a dominant theory must withstand scrutiny from all sides. The modified gravity proposals have pushed researchers to gather better data and sharpen their theories, which is a win for science either way. As of now, the evidence strongly points to some kind of unseen mass in the universe. The big question is not so much, does dark matter exist? The consensus says yes, but rather, what exactly is dark matter? And on that front, we are still in the dark. To truly answer that, we need to catch the dark matter in the act, detect its particles, if they are particles, and pin down their properties. That's the next phase of this grand investigation. In laboratories deep underground, in giant particle accelerators, and in observatories watching the skies, scientists have been mounting a concerted hunt for the particles of darkness. Our journey will continue into that search as we strive to bring the shadowy substance of the cosmos into the light.